Hello there. Tonight, we are not just looking at the universe. We're stepping into the part of it that refuses to be seen. The stars above you, the galaxies stretching across the night, all of it feels vast, powerful, almost overwhelming. But here is the quiet truth that few truly stop to feel. What you can see is almost nothing. 95% of this universe exists in silence, in darkness, in something we cannot touch, cannot see, and yet cannot escape. Dark matter, dark energy, invisible forces that hold galaxies together, and at the same time, slowly pull the entire universe apart. This is not a loud story. There are no explosions here, no chaos. Only a deep, steady presence shaping everything from the shadows. And as you listen, as your mind begins to slow, you'll start to feel it differently. Not as something distant, but as something real, something surrounding you, something moving through you even now. Because this is not just the story of the universe. It is the story of the unseen reality you're already inside. So let your thoughts drift, let your breathing settle, and allow yourself to sink into this quiet, endless expanse. But before we begin, if you find something here that pulls you in, something that makes you pause, think, or simply feel calm, take a moment gently to like this video. And if you want more journeys like this, deep, slow, and quietly powerful, consider subscribing to the channel. No rules, no pressure, just a quiet invitation waiting for you. Now, close your eyes if you'd like, and let's step into the darkness together. Chapter 1: The Invisible Universe. Understanding what we cannot see. There's a quiet truth about the universe that often goes unnoticed, something so vast and so fundamental that it reshapes everything we think we understand about reality. As you begin to settle into this journey, imagine looking up at the night sky, seeing stars scattered like distant embers, galaxies glowing softly across unimaginable distances. It feels complete, almost overwhelming in its beauty. And yet, what you're seeing, every star, every planet, every glowing nebula, makes up only a tiny fraction of what actually exists. In fact, the visible universe, everything that emits or reflects light, account for less than 5% of the total cosmic content. The remaining 95% is composed of something far more elusive, something that does not shine, does not reflect, and does not interact with light in any way we could directly observe. This is where the story of dark matter and dark energy begins, a story not of what we can see, but of what we can only infer. The idea that most of the universe is invisible may seem unsettling at first, but it emerged gradually, like a shadow revealing itself at the edge of perception. Scientists did not set out to discover dark matter. Instead, they stumbled upon it while trying to understand the motion of galaxies. When astronomers first began measuring how stars move within galaxies, they expected those stars to behave in a predictable way. Much like planets orbiting a star, objects farther from the center should move more slowly, influenced by the gravitational pull of visible matter. But what they found was something entirely different. Stars at the outer edges of galaxies were moving just as fast as those near the center, as if held in place by an unseen force. This unexpected motion hinted at the presence of a hidden mass, something that exerted gravity but could not be seen. It was as if galaxies were embedded in vast halos of invisible material, extending far beyond the stars themselves. This unseen substance became known as dark matter. Dark matter does not emit light, absorb light, or reflect light. It is completely invisible across the entire electromagnetic spectrum, and yet its presence is undeniable because of the gravitational influence it exerts. It acts as a cosmic scaffold, holding galaxies together and shaping the large-scale structure of the universe. To truly understand how strange this is, consider this. If dark matter did not exist, galaxies as we know them would simply fall apart. The stars would drift away into space, unable to remain bound by the gravity of visible matter alone. The universe would look entirely different, less structured, less organized, and perhaps far less capable of supporting the formation of complex systems like stars, planets, and ultimately life. But dark matter is only part of the story. As scientists continued to study the universe, they made another astonishing discovery, one that would challenge our understanding of cosmic expansion itself. The universe, it turns out, is not just expanding. It is accelerating in its expansion, as if driven by a mysterious force, pushing everything apart at an ever-increasing rate. This force is what we now call dark energy. Unlike dark matter, which pulls things together through gravity, dark energy does the opposite. It pushes space itself apart, stretching the fabric of the universe in a way that defies intuitive understanding. And just like dark matter, dark energy cannot be seen directly. Its presence is inferred through its effects, particularly the way distant galaxies appear to be moving away from us faster and faster over time. Together, dark matter and dark energy dominate the cosmos. They shape its past, define its present, and will ultimately determine its future. And yet, we still do not fully understand what they are. This is what makes the universe so quietly mesmerizing. Beneath the calm glow of distant stars lies a deeper reality, one that is largely hidden from view. It is a universe governed not just by what we can observe, but by what we cannot. As you continue to drift through these thoughts, imagine the universe not as a brightly lit stage, but as a vast, dimly illuminated ocean. The stars are like small islands of light, scattered across an immense darkness. Beneath the surface, unseen currents shape everything, guiding the motion of galaxies, influencing the birth of stars, and determining the ultimate fate of the cosmos. One of the most fascinating aspects of dark matter is how it interacts, or rather, how it does not interact with ordinary matter. Unlike the atoms that make up everything we see and touch, dark matter does not collide, does not stick, and does not form structures like planets or stars. It passes through ordinary matter almost completely undisturbed, like a ghost moving silently through walls. In fact, trillions of dark matter particles may be passing through your body right now, without you ever noticing. They leave no trace, create no sensation, and yet they are part of the same universe you inhabit. This realization brings a certain stillness to the mind. The idea that there is so much happening around us beyond our senses invites a different kind of awareness. It reminds us that reality is far deeper and more complex than it appears on the surface. And then there is dark energy, even more mysterious, even more abstract. While dark matter can be thought of as a hidden substance, dark energy is something else entirely. It is not a material in the traditional sense. Instead, it seems to be a property of space itself, an intrinsic energy that permeates every corner of the universe. As space expands, more of it comes into existence, and with it, more dark energy. This creates a kind of feedback loop where expansion leads to more energy, which leads to even faster expansion. It is a quiet, relentless process unfolding over billions of years. If you were to observe the universe on a timescale far beyond human comprehension, you would see galaxies drifting farther and farther apart, the night sky gradually growing darker as distant stars move beyond the reach of our observation. Eventually, the universe could become a place of profound isolation, where each galaxy exists alone in an ever-expanding void. But for now, we are still in a moment of connection, a moment where the light from distant galaxies continues to reach us, carrying with it the story of the cosmos. As you let these ideas settle, there is no need to rush toward understanding. The beauty of this subject lies not in having all the answers, but in quietly exploring the questions. The universe does not reveal itself all at once. It unfolds slowly, like a story told across billions of years. And perhaps that is what makes it so perfect for a calm, drifting mind. The realization that there is more, so much more, than what we can see. A universe filled with invisible structures, silent forces, and hidden energies. A universe that is in many ways still waiting to be understood. As the quiet vastness of a universe continues to unfold in your mind, there is a gentle shift that begins to happen. What once felt empty, those immense stretches of darkness between galaxies, starts to take on a different meaning. It is no longer just absence. It becomes presence of another kind, something subtle, something deeply influential, yet forever out of direct reach. One of the most fascinating truths about dark matter is that it began shaping the universe long before stars ever existed. In the earliest moments after the Big Bang, the universe was an incredibly hot and dense sea of particles and radiation. Everything was chaotic, almost uniform, with only the tiniest fluctuations in density, imperfections so small they might seem insignificant. And yet, those slight variations became the seeds of everything that would follow. Dark matter, unlike ordinary matter, did not interact with radiation. While normal particles were constantly scattering light, unable to settle in a structure, dark matter moved quietly through this early universe, unaffected by that intense radiation. It began to clump together under its own gravity, forming invisible scaffolding, vast, diffuse halos that would later guide the formation of galaxies. This is one of the most remarkable aspects of dark matter. It came first. Before the first stars ignited, before galaxies spun into existence, dark matter had already begun laying down the framework of the cosmos. Ordinary matter, slowed down by its interaction with light, eventually fell into these dark matter wells, gathering and condensing until stars and galaxies were born. In this way, every galaxy you can see is, in a sense, sitting inside an invisible structure. It is like a glowing city built within a vast, transparent architecture that extends far beyond its visible edges. Another quiet truth is how unevenly distributed dark matter is. It is not spread smoothly across the universe. Instead, it forms a kind of cosmic web, a vast network of filaments stretching across unimaginable distances. At the intersections of these filaments, galaxies cluster together, forming groups and clusters that can contain thousands of galaxies bound by gravity. Between these filaments lie enormous voids, regions of space where very little matter exists at all. These voids are among the largest structures in the universe, spanning hundreds of millions of light years. And yet, even within them, dark energy continues its subtle work, expanding space itself. The cosmic web is not something we can see directly, but its presence has been mapped through careful observation and simulation. By studying how galaxies are distributed and how light bends as it travels through space, scientists have been able to reconstruct this hidden structure with remarkable precision. This bending of light brings us to another extraordinary phenomenon: gravitational lensing. When light from a distant galaxy passes near a massive object, such as a cluster of galaxies filled with dark matter, its path is bent by gravity. This effect can magnify, distort, or even duplicate the image of the background galaxy. It is as if space itself becomes a lens, shaped by the presence of mass. What makes gravitational lensing so powerful is that it allows us to see dark matter indirectly. By observing how light is bent, scientists can map the distribution of mass, even when that mass is completely invisible. In many cases, these maps reveal far more mass than what is visible, confirming again that most of the universe is hidden. There is something almost poetic about this. Light, traveling across billions of years, quietly curves around something it cannot reveal directly, leaving behind subtle clues for those who know how to look. And then there are galaxy clusters, the largest gravitationally bound structures in the universe. These clusters provide some of the strongest evidence for dark matter. When astronomers measure the mass of these clusters based on the motion of galaxies within them, they find far more mass than can be accounted for by visible matter alone. One famous example is the Bullet Cluster, where two galaxy clusters have collided. In this event, the ordinary matter, mostly hot gas, interacted and slowed down, while the dark matter passed through almost unaffected. By observing the separation between visible matter and gravitational mass, scientists were able to clearly distinguish between the two, providing compelling evidence that dark matter is something fundamentally different from ordinary matter. While dark matter shapes structure, dark energy shapes destiny. The discovery of dark energy came from observing distant supernovae, exploding stars that serve as cosmic markers. By measuring how bright these explosions appeared, scientists could estimate how far away they were. What they found was surprising. Distant supernovae were dimmer than expected, suggesting they were farther away than predicted. This meant that the expansion of the universe was not slowing down, as previously thought, but accelerating. This discovery, made in the late 20th century, changed everything. It revealed that there is a force, something deeply woven into the fabric of space, that is driving galaxies apart at an increasing rate. Dark energy now appears to make up about 70% of the universe, making it the dominant component of cosmic reality. And yet, it remains one of the greatest mysteries in all of science. Some theories suggest that dark energy is related to the energy of empty space itself, often referred to as vacuum energy. Others propose that it could be a dynamic field, changing over time. There are even ideas that it might indicate a need to revise our understanding of gravity on the largest scales. But for now, it remains an open question. As you continue to drift through these ideas, there's a certain calm in accepting that not everything needs to be fully understood. The universe is vast, and its mysteries are deep. Each discovery opens the door to new questions, new possibilities, and new ways of seeing. Another quiet truth is that despite all our technological advancements, we are still only at the beginning of this journey. Experiments around the world are searching for direct evidence of dark matter particles, using highly sensitive detectors placed deep underground to shield them from interference. So far, these experiments have not yet confirmed a definitive detection, but they continue to refine our understanding, narrowing down the possibilities. At the same time, telescopes are mapping the universe with increasing detail, revealing the large-scale structure shaped by dark matter and dark energy. Observatories studying the cosmic microwave background, the faint afterglow of the Big Bang, provide a snapshot of the universe when it was only a few 100,000 years old, offering clues about its composition and evolution. All of this points to a universe that is both knowable and mysterious, structured and unpredictable. And perhaps that is the most comforting thought of all, that even in a universe dominated by invisible forces, there is a kind of quiet order, a set of patterns and principles that allow us to explore, to question, and to understand, even if only partially. As the mind begins to settle, you can imagine yourself drifting through this vast cosmic ocean, surrounded not just by stars, but by the unseen currents of dark matter and the gentle expansion driven by dark energy. There is no urgency here, no need to reach a conclusion, only the steady unfolding of a universe that is far larger, far deeper, and far more mysterious than it first appears. And as you rest within that thought, the invisible becomes just a little more familiar. Chapter 2. The First Clues. How dark matter was discovered. There is something quietly compelling about the way great discoveries often begin, not with certainty, but with confusion. A small inconsistency, a subtle mismatch between expectation and observation, and a question that refuses to fade. The story of dark matter begins in just such a way, not with a sudden revelation, but with a lingering sense that something in the universe was not behaving as it should. In the early 20th century, astronomy was undergoing a transformation. Telescopes were becoming more powerful, measurements more precise, and for the first time, scientists were beginning to explore the universe beyond our own galaxy in meaningful detail. It was a time of careful observation, of patience, of long nights spent tracing faint points of light across photographic plates. And within those observations, the first hints of something unseen began to emerge. One of the earliest figures to notice this discrepancy was Fritz Zwicky, a Swiss astronomer working in the 1930s. Zwicky was studying a large collection of galaxies known as the Coma Cluster, a massive grouping located hundreds of millions of light-years away. At the time, astronomers were trying to understand how such clusters held themselves together. Using the principles of gravity, Zwicky measured how fast the galaxies within the cluster were moving. These galaxies were not still. They were orbiting the center of the cluster at high speeds, influenced by the gravitational pull of the mass within it. By calculating these speeds, he could estimate how much mass was required to keep the cluster bound together. But what he found was deeply puzzling. The galaxies were moving far too quickly. If only the visible matter, the stars and gas within those galaxies, were providing the gravitational pull, the cluster should have flown apart. The galaxies should have escaped into space, unable to remain bound by such a weak gravitational force. And yet, the cluster remained intact. To explain this, Zwicky proposed that there must be additional mass, something unseen, something that did not emit light. He called it Dunkel Materie, or dark matter. At the time, his idea was not widely accepted. It seemed too speculative, too uncertain. After all, astronomy had always relied on what could be observed, measured, and directly studied. Suggesting that most of the mass in the universe was invisible felt like a step too far. And so, for decades, the idea remained in the background, a curious possibility, but not yet a central pillar of cosmology. It would take another set of observations, several decades later, to bring dark matter back into focus. In the 1970s, an astronomer named Vera Rubin began studying the rotation of spiral galaxies. These galaxies, with their graceful, swirling arms, provided an ideal laboratory for understanding how matter is distributed within them. Working alongside her collaborator Kent Ford, Rubin measured how fast stars were moving at different distances from the centers of galaxies. According to classical physics, stars farther from the center should move more slowly, much like planets in our solar system. The gravitational pull weakens with distance, and so the outer stars should drift more gently through space. But once again, the universe had other plans. What Rubin found was not a decline in speed, but a surprising consistency. Stars at the outer edges of galaxies were moving just as fast as those closer to the center. The rotation curves, graphs showing speed versus distance, remained flat instead of dropping off. This was not a small discrepancy. It was a clear, persistent pattern observed across many galaxies. And the implication was unavoidable. There had to be more mass than what was visible. Unlike Zwicky's earlier work, Rubin's findings were difficult to ignore. The data was precise, the pattern consistent, and the conclusions compelling. Slowly, the idea of dark matter began to gain acceptance within the scientific community. It was no longer just a theoretical curiosity. It was becoming a necessary component of our understanding of the universe. Another quiet but important clue came from the study of galaxy clusters and the hot gas within them. These clusters contain vast amounts of gas heated to extremely high temperatures, emitting X-rays that can be detected by space-based observatories. By analyzing this gas, scientists can estimate the total mass required to keep it gravitationally bound within the cluster. Once again, the numbers did not add up. There was far more mass implied by the gravitational effects than could be accounted for by visible matter alone. The same pattern appeared again and again across different scales and different methods of observation. It was as if the universe was gently repeating the same message over and over. There is more here than you can see. As these observations accumulated, the concept of dark matter began to shift from speculation to necessity. It became clear that without this invisible component, many of the structures we observe simply could not exist in their current form. Galaxies would not hold together. Clusters would disperse. The large-scale structure of the universe, the cosmic web of filaments and voids, would not have formed in the way we observe today. Another piece of evidence came from the study of the cosmic microwave background, the faint afterglow of the early universe. This radiation carries within it tiny fluctuations, variations in temperature that reflect the distribution of matter in the universe shortly after the Big Bang. By analyzing these fluctuations, scientists can determine the overall composition of the universe. And what they found was striking. The amount of ordinary matter, atoms, stars, gas, was far too small to account for the observed structure. There had to be an additional component, one that interacted gravitationally but not with light. This aligned perfectly with the idea of dark matter. As you let these discoveries settle into place, there is a sense of gradual unfolding. No single observation proved the existence of dark matter on its own. Instead, it was the convergence of many lines of evidence, each pointing in the same direction, each reinforcing the others. It is a reminder that understanding often comes not from one moment of clarity, but from the steady accumulation of insight. And there's something deeply calming in that process. The universe does not rush. It reveals itself slowly, patiently, allowing us to piece together its mysteries over time. Even now, as you imagine these early astronomers peering into the night sky, measuring faint glimmers of light, there is a quiet continuity between their work and our own curiosity. They were searching for answers, just as we are, guided by observation, shaped by wonder. And what they found was not just a new component of the universe, but a new way of thinking about it. A universe where the unseen is not empty, but essential. A universe where absence can hold as much meaning as presence. A universe that invites us to look deeper, to question more, and to embrace the unknown. As the story continues to unfold, there is a gentle sense that the universe is not revealing its secrets in sudden bursts, but rather in quiet confirmations. One observation reinforcing another, like soft echoes across vast distances of time and space. By the late 20th century, the idea of dark matter was no longer an isolated hypothesis. It had become a thread woven through multiple areas of astronomy, each one pointing toward the same unseen presence. One of the most elegant confirmations came through a phenomenon that feels almost dreamlike in its simplicity: light bending through space. According to general relativity, massive objects can curve the fabric of space-time, causing light to follow a slightly altered path. This effect, known as gravitational lensing, allows astronomers to detect mass not by seeing it directly, but by observing how it distorts the light from objects behind it. When scientists began mapping galaxies and clusters using gravitational lensing, they discovered something remarkable. The amount of mass required to produce the observed distortions was far greater than what could be accounted for by visible matter alone. In many cases, the lensing maps revealed vast halos of mass extending well beyond the luminous parts of galaxies. It was as though the visible universe was only the glowing tip of something much larger, something hidden yet undeniably present. This method offered an independent confirmation of dark matter, one that did not rely on a motion of stars or galaxies, but on the behavior of light itself. And once again, the conclusion was the same. There is more mass in a universe than we can see. Another important step in this unfolding story came from large-scale surveys of galaxy distribution. As astronomers mapped the positions of millions of galaxies, a pattern began to emerge. Galaxies were not scattered randomly. Instead, they formed intricate structures, filaments, walls, and clusters, surrounding vast empty regions known as voids. This structure, often referred to as the cosmic web, matched closely with theoretical models that included dark matter. Without dark matter, these structures would not have had enough time to form since the Big Bang. The gravitational pull of ordinary matter alone would have been too weak, too slow to create such complexity within the age of the universe. Dark matter, however, provided the missing ingredient. Its gravitational influence accelerated the formation of structure, allowing galaxies and clusters to emerge much earlier than they otherwise could have. There is something quietly reassuring about this alignment between theory and observation. It suggests that, even in the face of the unknown, there's a kind of underlying coherence, a pattern that can be traced, understood, and appreciated. Yet, even as the evidence for dark matter grew stronger, its true nature remained elusive. Scientists began to ask a deeper question. If dark matter exists, what is it made of? This question led to a wide range of theoretical possibilities. One of the earliest ideas was that dark matter might consist of faint, ordinary objects, things like brown dwarfs, neutron stars, or black holes that simply do not emit much light. These were collectively referred to as machos, or massive astrophysical compact halo objects. For a time, this seemed like a plausible explanation. After all, if there were enough of these dim objects scattered throughout galaxies, they could account for the missing mass. But as observational techniques improved, this idea began to lose ground. Surveys looking for these objects through gravitational microlensing, brief brightening events caused when a massive object passes in front of a distant star, found that there simply were not enough of them to explain the full extent of dark matter. The focus then shifted to a different class of candidates, WIMPs, or weakly interacting massive particles. These hypothetical particles would not interact with light, making them invisible, but would still exert gravitational influence. They would pass through ordinary matter almost undisturbed, much like dark matter is expected to do. WIMPs became one of the leading candidates, and scientists around the world began designing experiments to detect them directly. Deep underground laboratories were constructed, shielded from cosmic rays and background noise, in the hope of capturing the faintest possible interaction between a dark matter particle and a detector. So far, these experiments have not yet provided a definitive detection, but each result helps refine our understanding, narrowing the range of possibilities and guiding future research. There is a quiet patience in this process, a recognition that some questions require time, decades, even centuries to answer. Another intriguing possibility is that dark matter might not be a particle at all, but rather a sign that our understanding of gravity is incomplete. Some alternative theories propose modifications to the laws of gravity at very large scales, suggesting that what we interpret as dark matter could instead be a different behavior of gravity itself. While these ideas are still being explored, most evidence continues to support the existence of dark matter as a distinct component of the universe. The consistency across multiple lines of observation, galaxy rotation curves, cluster dynamics, gravitational lensing, and cosmic background radiation creates a compelling case. And yet, the mystery remains. As you let these thoughts settle, there's a certain calm in accepting that the universe is not fully known, that even with all our knowledge, there are still vast regions of uncertainty waiting quietly to be explored. Another subtle but important clue comes from computer simulations. By modeling the universe using known laws of physics and including dark matter, scientists can recreate structures that closely resemble what we observe. Galaxies form, clusters emerge, and the cosmic web takes shape in a way that mirrors reality. Without dark matter, these simulations fail to produce the same level of structure. The universe remains too smooth, too uniform, lacking the complexity we see in the real cosmos. This alignment between simulation and observation provides yet another layer of evidence, reinforcing the idea that dark matter is not just a theoretical construct, but a fundamental part of the universe. and still, it remains invisible. There is something deeply poetic about that. The idea that most of the universe exists beyond our direct perception, shaping everything we see without ever revealing itself fully. It invites a different kind of awareness, one that is less focused on certainty and more open to possibility. As the mind begins to relax, you can imagine the universe as a vast, layered reality. The visible world, the stars, the galaxies, the glowing clouds of gas, is just one layer. Beneath it lies another, quieter layer, made of dark matter, guiding structure and motion. And beyond that, an even deeper layer, shaped by dark energy, gently stretching the fabric of space itself. Each layer interacts with the others, creating the universe as we experience it. And yet, each layer also holds its own mysteries, its own unanswered questions. There is no need to resolve them all at once. The beauty lies in the exploration, in the slow unfolding of understanding, in the quiet realization that the universe is far more intricate than it first appears. And as you drift through these thoughts, there is a sense of connection, not just to the stars above, but to the deeper, unseen forces that shape them. A universe filled not only with light, but with shadow, not only with what is known, but with what is still waiting to be discovered. Chapter 3: Galaxies in Motion. The hidden mass that holds them together. There's a quiet elegance in the way galaxies move. If you imagine a spiral galaxy from afar, it appears almost like a slow, cosmic dance, its arms gently curving outward, stars tracing long, graceful paths around a luminous center. There is no sound in this motion, no friction, no turbulence in the way we might expect. Just a steady, enduring rotation, unfolding over hundreds of millions of years. At first glance, it seems simple enough. Gravity holds everything together. Stars orbit the center, much like planets orbit a star. But when astronomers began to look more closely, measuring these motions with increasing precision, they discovered something deeply unexpected, something that would once again point toward the invisible. To understand this, it helps to picture how motion should behave under normal circumstances. In systems governed only by visible matter, objects farther from the center experience weaker gravitational pull. This means they should move more slowly. In our own solar system, for example, planets like Mercury orbit very quickly, while distant planets like Neptune move much more slowly. This predictable relationship is described by classical mechanics and has been confirmed countless times. But galaxies do not follow this pattern. When scientists measured the rotational speeds of stars at different distances from the centers of spiral galaxies, they found something striking. Instead of slowing down, the stars maintained nearly constant speeds, even far out in the outer regions where visible matter becomes sparse. These measurements are known as rotation curves. And instead of showing a decline, these curves remain flat. This is one of the most important clues in the study of dark matter. Because for stars to maintain such high speeds at large distances, there must be additional gravitational pull, far more than what visible matter can provide. It is as though galaxies are embedded in massive, invisible halos that extend well beyond their visible edges. These halos are not small. In fact, they can be several times larger than the galaxies themselves. While the luminous disk of a galaxy may span tens of thousands of light years, the dark matter halo surrounding it can stretch hundreds of thousands of light years into space. And within these halos lies the majority of the galaxy's mass. This realization transforms the way we think about galaxies. They are not just collections of stars and gas. They are structures defined and dominated by something unseen, something that provides the gravitational backbone holding everything together. Another fascinating aspect of this hidden mass is how smoothly it is distributed. Unlike ordinary matter, which tends to clump into dense objects like stars and planets, dark matter forms diffuse, extended structures. It does not collapse into compact forms because it does not lose energy through interactions like radiation. Instead, it remains spread out, creating a kind of invisible envelope around galaxies. This smooth distribution is what allows it to influence the motion of stars across such large distances. If dark matter were concentrated only in the center, we would still see a drop-off in rotational speed. But because it extends outward, its gravitational influence remains strong even in the farthest reaches of a galaxy. As you let this idea settle, there is something almost calming about the consistency of it. The universe, despite its vastness, follows patterns that reveal themselves slowly through careful observation and patient understanding. Another layer of this story comes from studying different types of galaxies. Not all galaxies are spiral. Some are elliptical, appearing more like glowing spheres, while others are irregular, lacking a defined shape. And yet, across these different forms, the influence of dark matter remains consistent. In elliptical galaxies, the motion of stars is more random, moving in all directions rather than in a flat disk. But when scientists analyze these motions, they still find evidence of far more mass than what is visible. In dwarf galaxies, small, faint galaxies containing relatively few stars, the effect of dark matter is even more pronounced. These galaxies often appear to be dominated almost entirely by dark matter, with visible matter making up only a small fraction of their total mass. It is as if dark matter provides the framework, and visible matter simply fills in the details. One particularly interesting case involves satellite galaxies, small galaxies that orbit larger ones, much like moons orbit planets. The motion of these satellites provides additional clues about the distribution of mass in a larger galaxy. By tracking how these smaller galaxies move, scientists can infer the gravitational field of the larger system. And once again, the results point to the presence of extended dark matter halos, far beyond what can be seen. There is a quiet repetition in these observations, a steady reinforcement of the same idea across different scales and systems. And then there are galaxy collisions. When galaxies interact or merge, their behavior provides yet another window into the role of dark matter. During these events, stars within the galaxies rarely collide directly due to the vast distances between them. Instead, they pass by each other, influenced by gravity. But the overall structure of the galaxies, how they distort, merge, and eventually settle, depends heavily on the distribution of mass, including dark matter. Simulations of galaxy collisions that include dark matter match observations remarkably well. Without dark matter, the outcomes look very different, lacking the same structure and dynamics. This again reinforces the idea that dark matter is not just an optional component. It is essential. As the mind continues to drift through these concepts, there's a sense of quiet coherence. The same invisible presence appears in rotation curves, in galaxy shapes, and satellite motions, in collisions. It is not confined to one observation or one method. It is woven throughout the entire fabric of galactic behavior, and yet it remains unseen. Another subtle but important detail is how dark matter influences the formation of galaxies themselves. In the early universe, small fluctuations in density began to grow under the influence of gravity. Dark matter, being unaffected by radiation, was able to collapse into these fluctuations more quickly than ordinary matter. This created gravitational wells, regions where matter could accumulate. Ordinary matter eventually fell into these wells, cooling and forming stars. In this way, dark matter did not just shape galaxies after they formed. It played a crucial role in their very creation. Without dark matter, galaxies might not have formed at all, or at least not in the way we observe today. This adds another layer to its importance. It is not just holding galaxies together. It is responsible for their existence in the first place. As you imagine this process unfolding over billions of years, there is a quiet sense of scale, of time stretching far beyond human experience, of structures forming slowly, guided by forces that operate silently in the background. The universe does not rush. It builds layer by layer, guided by gravity, shaped by the unseen. And within that process, dark matter plays its quiet, essential role, holding galaxies together, guiding their motion, shaping their formation, all without ever revealing itself directly. As the motion of galaxies continues to unfold in your thoughts, there is a quiet realization that what we observe is only part of the story. Beneath the visible glow of stars lies a deeper structure, one that does not shimmer or shine, but instead quietly governs the rhythm of everything we see. When astronomers map the motion of stars and galaxies with increasing precision, they begin to notice subtle patterns beyond the flat rotation curves. These patterns reveal that dark matter halos are not perfectly uniform. Instead, they have gentle variations in density, regions where dark matter is slightly more concentrated and others where it is more diffuse. These variations influence how galaxies evolve over time. For instance, in some galaxies, the central regions appear less dense than expected, forming what scientists call cores rather than steep cusps. This has led to ongoing discussions about how dark matter behaves on smaller scales, and whether interactions, either with itself or with ordinary matter, might play a role in shaping these inner regions. It is a reminder that even within something as elusive as dark matter, there are layers of complexity still waiting to be understood. Another fascinating aspect is how dark matter affects the stability of galactic structures. Spiral arms, those long, graceful features extending outward from the centers of galaxies, are not fixed objects. They are patterns, waves of higher density moving through the disk of stars and gas. Dark matter contributes to the overall gravitational potential that allows these patterns to form and persist. Without it, the delicate balance required to maintain spiral structures would be disrupted, and galaxies might appear far more chaotic. This influence extends even further when we consider bars, elongated structures found in the centers of many spiral galaxies. These bars act as channels, funneling gas toward the central regions and often triggering bursts of star formation. The presence and behavior of these bars are closely tied to the distribution of mass within the galaxy, including dark matter. A more massive halo can stabilize the disk, affecting how and when such structures form. As you imagine these slow, graceful processes unfolding over millions of years, there's a sense of quiet continuity. Galaxies are not static. They're living systems, evolving, interacting, and reshaping themselves under the influence of both visible and invisible forces. And then there are dwarf galaxies, some of the smallest and faintest galaxies in the universe, yet among the most revealing when it comes to understanding dark matter. These galaxies often contain very few stars, making their visible mass relatively small. And yet, when astronomers measure how stars move within them, they find that these motions require far more mass than what is visible. In some cases, dwarf galaxies appear to be composed almost entirely of dark matter, with ordinary matter playing only a minor role. This makes them valuable laboratories for studying dark matter in a relatively clean environment, where its effects are not masked by large amounts of visible material. Interestingly, some dwarf galaxies orbit larger galaxies like the Milky Way, forming a kind of extended family of smaller companions. By observing how these dwarf galaxies move, scientists can infer the shape and extent of the Milky Way's dark matter halo. These observations suggest that our galaxy is surrounded by a vishal, roughly spherical halo of dark matter, extending far beyond the visible disk of stars. It is within this halo that our solar system quietly resides, moving along with the rest of the galaxy. Another subtle but important phenomenon is known as dynamical friction. When a massive object, such as a galaxy or a cluster, moves through a field of dark matter, it experiences a kind of resistance, not like friction in the traditional sense, but a gravitational effect. As the object moves, it creates a wake in the distribution of dark matter behind it, which in turn exerts a pull, slowing the object down over time. This process plays a role in galaxy mergers, helping to bring galaxies together and allowing them to eventually combine into larger structures. It is another example of how dark matter, though invisible, actively shapes the evolution of cosmic systems. There is also growing interest in how dark matter might behave on even smaller scales. Some theories suggest that dark matter could form tiny clumps or substructures within larger halos. These subhalos might host small galaxies, or in some cases, remain completely dark, containing no stars at all. Detecting these substructures is challenging, but techniques such as gravitational lensing offer a possible path forward. By observing subtle distortions in light, scientists can search for the presence of these otherwise invisible clumps. This adds another layer to the cosmic landscape, one where not only galaxies, but entire invisible structures exist within larger frameworks. As you continue to drift through these ideas, there's a sense of depth, of layers within layers, each one contributing to the whole. Another intriguing detail is how dark matter influences the motion of gas within galaxies. Gas clouds, unlike stars, can collide and interact, leading to complex behaviors such as shock waves, turbulence, and star formation. The gravitational potential created by dark matter shapes how this gas moves, where it accumulates, and how it eventually collapses to form new stars. In this way, dark matter indirectly influences the life cycle of stars themselves. Even the formation of supermassive black holes at the centers of galaxies may be connected, in part, to the distribution of dark matter. While the exact relationship is still being studied, the overall mass and structure of a galaxy, including its dark matter halo, appear to play a role in how these massive objects grow over time. There is something quietly profound about this interconnectedness. Dark matter, though unseen, influences stars. Stars influence gas. Gas forms new stars. Galaxies evolve. And all of it unfolds within the same vast, interconnected system. Another gentle realization is how stable these systems are. Despite the immense forces at play, galaxies can persist for billions of years, maintaining their structure, their motion, and their identity. This stability is made possible, in large part, by the gravitational framework provided by dark matter. Without it, the delicate balance that holds galaxies together would be disrupted, and the universe might look very different, less ordered, less structured, less capable of sustaining the complex systems we observe. As the mind begins to slow, there is a sense of quiet appreciation for this hidden structure, the idea that something invisible can be so essential, that what we do not see can shape what we do, that the universe is not just a collection of glowing objects, but a deeply layered reality, guided by forces that operate silently in the background. And as you imagine galaxies continuing their slow, graceful motion, stars orbiting, arms turning, clusters drifting, you can also imagine the invisible halo surrounding them, holding everything gently in place. There is no rush in this movement, no urgency, only the steady, timeless rhythm of a universe shaped by both light and shadow. And within that rhythm, dark matter remains, quiet, constant, and essential. Chapter 4. Mapping the Unseen. Dark matter across the cosmic web. There is a moment when thinking about the universe on its largest scales, where the mind begins to stretch beyond familiar boundaries. Galaxies are no longer isolated islands of light, but part of something far greater, an intricate, almost delicate structure that spans the entire cosmos. It is here, in this vast perspective, that dark matter reveals one of its most extraordinary roles. If you could step far outside the universe and look back at it, not as scattered points of light, but as a whole, you would not see randomness. Instead, you would see a pattern, a vast network of filaments stretching across unimaginable distances, connecting clusters of galaxies like threads in a cosmic tapestry. This structure is known as the cosmic web. It is one of the most profound discoveries in modern astronomy, and it exists largely because of dark matter. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. There were tiny fluctuations, slight variations in density, but overall, the universe was remarkably smooth. Over time, gravity began to amplify these small differences. Dark matter, unaffected by radiation, responded first. It began to collapse into these denser regions, forming long, filament-like structures. These filaments grew and stretched, connecting to one another, creating a vast network that would become the backbone of the universe's large-scale structure. Ordinary matter followed. Slowed down initially by its interaction with light, it eventually cooled and fell into the gravitational wells created by dark matter. At the intersections of these filaments, where the density was highest, galaxies began to form. Over billions of years, these regions grew into massive clusters, each containing hundreds or even thousands of galaxies. Between these filaments, vast voids emerged, regions where very little matter exists. These voids can span hundreds of millions of light years, making them some of the largest structures in the universe. And yet, even within these immense emptinesses, dark energy continues its quiet work, gently expanding space itself. Mapping this cosmic web is no simple task. Because dark matter cannot be seen directly, astronomers must rely on indirect methods to trace its presence. One of the most powerful of these methods is gravitational lensing. As light from distant galaxies travels toward us, it passes through regions of space filled with varying amounts of mass. Where dark matter is present, it bends the path of this light ever so slightly. By measuring these distortions across large areas of the sky, scientists can reconstruct detailed maps of mass distribution, including dark matter. These maps reveal a universe that is far from uniform. Instead, it is structured, interconnected, and deeply influenced by something invisible. There is something quietly beautiful about this process. Light, traveling across billions of years, carries with it the imprint of everything it has encountered. And by studying that light, we can uncover the hidden architecture of the cosmos. Another method involves observing the distribution of galaxies themselves. Galaxies tend to form in regions where dark matter is more concentrated. By mapping their positions, astronomers can infer the underlying dark matter structure. Large surveys involving millions of galaxies have allowed scientists to create three-dimensional maps of the universe, revealing the filamentary patterns of the cosmic web. These maps are not just static images. They tell a story of evolution, how the universe has grown and changed over time. In computer simulations, scientists can recreate this process from the very beginning. Starting with initial conditions based on observations of the cosmic microwave background, they allow gravity to act over billions of years. The result is a virtual universe that closely resembles what we observe today. Filaments form, clusters emerge, voids expand, and throughout it all, dark matter provides the underlying framework. Without it, these simulations fail to produce the same level of structure. The universe remains too smooth, lacking the intricate patterns we see in reality. This alignment between simulation and observation is one of the strongest pieces of evidence for dark matter's role in shaping the cosmos. But the cosmic web is not just a large-scale phenomenon. It also influences smaller structures, guiding the formation and evolution of individual galaxies. Galaxies do not form in isolation. They are fed by streams of gas flowing along dark matter filaments. These streams deliver the raw material needed for star formation, allowing galaxies to grow over time. In this way, the cosmic web acts as a kind of supply network, channeling matter across vast distances. There is a quiet efficiency in this process. Matter flows along invisible pathways, guided by gravity, shaping the universe in ways that are both subtle and profound. Another fascinating aspect of the cosmic web is how it evolves. In the early universe, the structure was less pronounced, with smaller fluctuations in density. Over time, these fluctuations grew, becoming more defined, more interconnected. Clusters became denser, filaments more distinct, voids larger. This process is still ongoing. Even now, billions of years after the Big Bang, the cosmic web continues to evolve. Galaxies merge, clusters grow, and the overall structure becomes more complex. And yet, there's also a counteracting force. Dark energy, the mysterious component driving the accelerated expansion of the universe, works against gravity. While dark matter pulls structures together, dark energy pushes them apart. This creates a delicate balance, one that shapes the ultimate fate of the cosmic web. As you imagine this interplay, there's a sense of quiet tension, of opposing forces shaping the same reality. Gravity pulling inward, expansion pushing outward, structure forming, even as space itself stretches. Another subtle truth is how vast these structures truly are. A single filament can span hundreds of millions of light years, connecting multiple galaxy clusters. The distances involved are so immense that even light, traveling at its maximum speed, takes millions of years to cross them. And yet, within this vastness, the same fundamental principles apply. Gravity, motion, structure, all guided by the unseen presence of dark matter. There is something deeply calming in recognizing this continuity, that the same laws govern both the smallest and largest scales, that the universe, despite its complexity, follows patterns that can be understood, explored, and appreciated. As the mind begins to drift, you can imagine yourself moving through this cosmic web, passing along vast filaments, drifting between clusters of galaxies, crossing immense voids where silence stretches for millions of light years. And all around you, though invisible, the presence of dark matter remains, shaping, guiding, holding the universe together in ways that are both subtle and profound. As the quiet structure of the cosmic web continues to unfold in your imagination, there is a gentle shift from seeing it as a static map to understanding it as something alive with motion, slow, immense, and almost timeless in its evolution. The universe is not frozen in place. It is flowing, expanding, and reshaping itself continuously, guided by forces both visible and unseen. One of the most fascinating truths about the cosmic web is that it is still forming, even now. Although billions of years have passed since the Big Bang, gravity continues to pull matter into denser regions. Filaments grow thicker, galaxy clusters become more massive, and smaller structures merge into larger ones. It is a process that unfolds over timescales so vast that it feels almost still, yet it is always in motion. This slow evolution is sometimes described as hierarchical growth. Small structures form first, and over time, they merge to create larger systems. Tiny clumps of dark matter attract ordinary matter, forming the earliest galaxies. These galaxies gather into groups, groups into clusters, and clusters into superclusters, all connected by the delicate threads of the cosmic web. There's a quiet order to this process, a sense that the universe is building itself step by step, layer by layer. Another remarkable aspect of the cosmic web is how it influences the direction in which galaxies spin. Observations suggest that the angular momentum of galaxies, the way they rotate, is not entirely random. Instead, it appears to be influenced by the orientation of the filaments in which they form. Galaxies embedded within these filaments often align their spin axes in relation to the larger structure around them. It is as though the cosmic web is not only shaping where galaxies form, but also how they move. This subtle alignment hints at a deeper connection between small-scale and large-scale structures, a kind of coherence that stretches across millions of light years. Another gentle truth emerges when we consider the role of gas within the cosmic web. While dark matter forms the backbone, ordinary matter, particularly hydrogen gas, flows along these filaments, feeding galaxies and fueling star formation. In some regions, this gas is heated to extremely high temperatures, forming vast reservoirs known as the warm, hot intergalactic medium. This medium is difficult to detect directly, but it is believed to contain a significant fraction of a universe's ordinary matter, matter that is not locked inside stars or galaxies, but instead drifts quietly through the spaces between them. It is another reminder that even the empty regions of the universe are not truly empty. They are filled with faint, diffuse matter, moving slowly along invisible pathways. And then there are the voids. At first, these vast regions might seem like simple absences, places where little has formed. But even voids have structure. They expand over time, becoming larger as matter flows outward toward denser regions. In a sense, voids are shaped just as much by dark matter as the filaments and clusters are. They are part of the same system, defined not by presence, but by relative absence, and both are essential to the overall shape of the universe. Another fascinating layer of understanding comes from the way we visualize the cosmic web through simulations. Modern supercomputers can model billions of particles representing dark matter, allowing scientists to watch the universe evolve from its earliest moments to the present day. These simulations produce intricate, web-like patterns that closely match what we observe through telescopes. One of the most well-known examples is the Millennium simulation, which revealed a universe filled with filaments, nodes, and voids, structures that emerge naturally when dark matter and gravity are included in the model. What is especially striking is how similar these simulated structures are to actual observations. It suggests that, despite the mystery surrounding dark matter's true nature, our understanding of its behavior is remarkably accurate on large scales. There is a quiet satisfaction in this alignment between theory and reality. Another subtle truth is how light travels through this cosmic web. As photons journey across the universe, they pass through regions of varying density. In denser areas, their paths are slightly bent, their travel times altered. In less dense regions, they move more freely. This creates a complex interplay of light and gravity, shaping the images we observe. In some cases, this leads to weak gravitational lensing, a slight distortion of galaxy shapes that can only be detected statistically by analyzing large numbers of galaxies. By studying these distortions, scientists can map the distribution of dark matter across vast regions of space. As dark energy drives space to expand, the distances between large structures increase. Over time, this expansion may become so dominant that the cosmic web itself begins to stretch apart, with clusters becoming isolated from one another. In the far future, galaxies outside our local group may move beyond the observable horizon, their light no longer able to reach us. The universe could become a much darker, more isolated place. But for now, we exist in a time where the cosmic web is still visible, still connected, still telling its story through the light that reaches us. There is something quietly meaningful about that. Another gentle realization is how much of this structure remains beyond our direct observation. Even with the most powerful telescopes, we can only see a portion of the observable universe. Beyond that lies more of the same, more filaments, more clusters, more voids, extending indefinitely. The cosmic web does not end where our vision does. It continues, vast and unbounded. As the mind begins to settle into this thought, there's a sense of calm in the scale of it all. The universe is not chaotic in the way it might first appear. It is structured, interconnected, and guided by underlying principles that give rise to both complexity and harmony. And at the heart of this structure lies dark matter. Invisible, silent, essential, holding together the threads of the cosmic web, shaping the paths of galaxies, guiding the flow of matter across unimaginable distances. As you drift through this vast network in your thoughts, there is no need to reach an end. The web continues, the universe expands, and within it all, the unseen remains, quietly shaping everything, even as it stays hidden from view. Chapter 5. The Nature of Darkness. What could dark matter be? There comes a point, as you continue to drift through the quiet vastness of the universe, where a deeper question begins to surface. It is no longer enough to know that dark matter exists, or that it shapes galaxies and structures across the cosmos. The mind naturally begins to wonder, what is it truly? What is this invisible presence that fills the universe, guiding everything, yet remaining just beyond our reach? This question has lingered for decades, resting at the intersection of astronomy and particle physics. And like many of the universe's most profound mysteries, it does not yield easily. Instead, it invites careful thought, patience, and a willingness to explore possibilities that stretch beyond everyday intuition. One of the first truths to understand is that dark matter is fundamentally different from ordinary matter. Everything we are familiar with, stars, planets, air, even the cells in your body, is made of atoms. These atoms interact with light, which is why we can see them. They absorb, emit, and reflect electromagnetic radiation, allowing them to be detected across the vast distances of space. Dark matter does none of this. It does not emit light. It does not absorb light. It does not reflect light. It exists entirely outside the electromagnetic spectrum, making it completely invisible to traditional observation. And yet, it has mass. This is perhaps the most important clue. Dark matter exerts gravity, influencing the motion of stars, galaxies, and even light itself. It behaves as though it is made of something real, something with substance. Yet it interacts in a way that is fundamentally different from anything we encounter in everyday life. This has led scientists to consider the possibility that dark matter is composed of entirely new kinds of particles. One of the most widely studied candidates is known as WIMPs, or weakly interacting massive particles. The idea behind WIMPs is both simple and elegant. These particles would have mass, allowing them to exert gravitational influence, but would interact only through the weak nuclear force and gravity. This would make them incredibly difficult to detect, as they would pass through ordinary matter almost entirely undisturbed. In fact, if WIMPs exist, they could be passing through your body right now, countless particles moving silently, leaving no trace, interacting so weakly that their presence is almost impossible to notice. There is something strangely calming about this idea. The notion that the universe is filled with invisible particles, moving gently through everything, shaping the cosmos without ever revealing themselves directly. Another intriguing possibility is the existence of axions. These are hypothetical particles that were originally proposed to solve a problem in quantum physics, but later emerged as a potential candidate for dark matter. Axions would be extremely light, far lighter than WIMPs, but could exist in enormous numbers, collectively contributing to the mass we attribute to dark matter. Unlike WIMPs, axions might be detectable through subtle interactions with electromagnetic fields, offering a different pathway for discovery. Experiments around the world are currently searching for these particles, using highly sensitive उपकरण designed to detect the faintest possible signals. These experiments operate in controlled environments, often shielded from external interference, allowing scientists to listen for whispers from the unseen. And yet, so far, dark matter has remained silent. Another class of candidates includes sterile neutrinos. Neutrinos themselves are already known to exist. They are incredibly light particles that rarely interact with matter, streaming through the universe, and through us, almost entirely unnoticed. Sterile neutrinos would be a heavier, even more elusive version of these particles, interacting only through gravity. If they exist, they could form part of the dark matter that fills the universe. But the search for dark matter is not limited to individual particles. Some theories suggest that dark matter could be composed of primordial black holes, tiny black holes formed in the early universe. These objects would not emit light, making them effectively invisible, but would still exert gravitational influence. While this idea is intriguing, current observations suggest that primordial black holes alone cannot account for all dark matter. Still, they remain a possibility worth exploring. There are also more exotic ideas. Some scientists propose that dark matter could be part of a hidden sector of physics, a parallel set of particles and forces that do not interact with our familiar world in the usual ways. This hidden sector could contain its own structures, its own dynamics, existing alongside our visible universe without direct interaction. It is a concept that feels almost philosophical. A universe within a universe. A layer of reality that exists, influences, and shapes, yet remains forever out of sight. As you let this idea settle, there's a sense of quiet wonder. The possibility that reality is deeper, more layered, more intricate than it first appears. Another important clue about dark matter comes from how it behaves. Unlike ordinary matter, which can collide, stick together, and lose energy, dark matter appears to be collisionless. This means that when dark matter particles encounter each other, they do not interact significantly. They pass through one another, maintaining their motion and distribution. This behavior is crucial for explaining the large-scale structure of the universe. It allows dark matter to form extended halos and filaments without collapsing into dense objects like stars. It also helps explain observations such as the bullet cluster, where dark matter and ordinary matter appear to behave differently during a collision. Another subtle but important property is that dark matter must be cold, or at least relatively slow-moving. If dark matter particles were moving too quickly, they would not be able to clump together effectively. The structures we observe, galaxies, clusters, the cosmic web, require dark matter to move slowly enough to form stable gravitational wells. This is why the leading models often refer to cold dark matter, emphasizing its role in structure formation. As the mind begins to relax into these possibilities, there is a sense of quiet openness. No single answer has been confirmed. No single theory has fully explained the nature of dark matter. And yet, each possibility adds a layer of understanding, a piece of the puzzle, guiding us slowly toward a deeper truth. There is no need to rush this process. The universe has taken billions of years to reach its current state. It is only natural that understanding it should take time as well. As you drift through these ideas, imagine the universe not just as a collection of stars and galaxies, but as a vast field of unseen particles, moving gently, shaping everything from within. Invisible, silent, and yet undeniably real. As the possibilities begin to settle in your mind, there's a quiet realization that the search for dark matter is not just about identifying a particle or confirming a theory. It is about expanding the boundaries of what we consider to be real. It asks us to accept that the universe may contain forms of matter entirely unlike anything we have ever directly experienced. And so, the search continues, patient, methodical, and deeply precise. Across the world, scientists have built experiments designed to detect even the faintest whisper of dark matter. Many of these experiments are placed deep underground, shielded by layers of rock to block out cosmic rays and background radiation. In these silent environments, detectors wait, sometimes for years, hoping that a single dark matter particle might pass through and leave behind the smallest trace of its presence. One such effort takes place at Gran Sasso National Laboratory, one of the largest underground laboratories in the world. Hidden beneath a mountain, it provides an environment so quiet that even the rarest interactions can, in principle, be detected. Inside these facilities, detectors are cooled to extremely low temperatures, sometimes close to absolute zero. At these temperatures, even the tiniest transfer of energy, perhaps from a passing dark matter particle, can be measured with incredible sensitivity. And yet, despite years of observation, the results have remained elusive. There have been hints, occasional signals that sparked excitement, but none have been confirmed beyond doubt. Each experiment refines the search, narrowing the range of possible properties that dark matter could have. There's a certain stillness in this process, a willingness to wait, to listen carefully to the quietest signals the universe might offer. Another approach to understanding dark matter involves high-energy particle accelerators, such as the Large Hadron Collider. Here, particles are accelerated to near the speed of light and collided with immense energy, recreating conditions similar to those just after the Big Bang. In these collisions, scientists look for signs of missing energy, evidence that particles have been produced but have escaped detection. Such particles could be candidates for dark matter. So far, no definitive discovery has been made, but each experiment provides valuable data, helping to refine theoretical models and guide future research. There is something quietly reassuring about this steady progress. Even in the absence of a clear answer, understanding deepens. Another intriguing line of research involves indirect detection. Instead of trying to observe dark matter particles directly, scientists look for the products of their interactions. If dark matter particles collide with each other or decay over time, they might produce detectable signals, such as gamma rays or other forms of high-energy radiation. Telescopes designed to detect these signals scan the sky, focusing on regions where dark matter is expected to be dense, such as the centers of galaxies. Occasionally, unusual signals are observed, excess emissions that cannot be easily explained by known processes. While these signals are intriguing, they remain inconclusive, requiring further study to determine their origin. And so, the mystery persists. Another general possibility is that dark matter might not be entirely passive. Some theories suggest that dark matter particles could interact with each other through forces other than gravity. These interactions would be extremely weak, but they could influence the way dark matter is distributed within galaxies. This idea, known as self-interacting dark matter, offers potential explanations for certain observations, such as the smoother density profiles seen in some galaxies. If true, it would mean that dark matter is not just a silent background presence, but something with its own subtle dynamics. There's something quietly fascinating about that thought. An invisible world with its own interactions, its own behaviors, existing alongside our own. Another emerging idea is that dark matter might be composed of ultra-light particles that behave more like waves than traditional particles. In this model, sometimes referred to as fuzzy dark matter, the particles have such low mass that their quantum nature becomes significant on galactic scales. This could lead to interference patterns, smoothing out structures, and affecting how galaxies form. It is a concept that blends the very small with the very large, quantum physics shaping the structure of entire galaxies. As you let this idea settle, there's a sense of quiet unity in the laws of physics. The same principles that govern the smallest particles may also shape the largest structures in the universe. Another subtle but important clue comes from the absence of detection. While this might seem like a lack of progress, it is actually quite informative. Each experiment that fails to detect dark matter rules out certain possibilities, narrowing the field of viable theories. It is like slowly carving away at a block of stone, revealing the shape within. The more we learn about what dark matter is not, the closer we come to understanding what it might be. There is a calm patience in this approach, a recognition that knowledge often grows through refinement, through careful elimination of possibilities. And then there is the broader perspective. What if dark matter is not a single thing, but a combination of different components? What if the universe contains multiple types of dark matter, each contributing in its own way? This idea, while more complex, reflects the richness of the universe itself. Just as ordinary matter exists in many forms, atoms, molecules, stars, planets, dark matter might also exist in a variety of forms, each with its own properties. It is a possibility that invites a sense of openness, a willingness to consider that the universe may be more diverse than we currently imagine. As the mind begins to slow, there's a gentle acceptance of the unknown. Dark matter remains one of the greatest mysteries in science, not because we lack evidence for its existence, but because its true nature continues to elude us. And yet, there is something deeply peaceful about that. The universe is not fully solved. It still holds secrets. It still invites exploration. As you drift through these thoughts, you can imagine scientists around the world working quietly in laboratories, observing the sky, refining their models, each step bringing us a little closer to understanding. There is no rush, only the steady unfolding of discovery. And somewhere, perhaps just beyond our current reach, the true nature of dark matter waits, silent, invisible, and profoundly woven into the fabric of the cosmos. Chapter 6, The Expanding Mystery, the discovery of dark energy. There is a certain stillness that comes when we think about the expansion of the universe. For a long time, it was believed to be a simple story, one that began with the Big Bang, when space itself burst outward from an incredibly dense state, setting galaxies in motion away from one another. The assumption seemed natural. Over time, gravity would act as a kind of cosmic brake, gradually slowing this expansion. It felt intuitive. After all, gravity pulls things together. It gathers matter, forms stars, binds galaxies. It seemed reasonable that, given enough time, this pull would begin to overcome the initial expansion, perhaps even reversing it someday. But the universe had something else in mind. In the late 20th century, astronomers began studying distant supernovae. explosions of dying stars so bright they can briefly outshine entire galaxies. These events, particularly a type known as type I supernovae, are incredibly useful because they have a consistent intrinsic brightness. This allows scientists to use them as standard candles, measuring their apparent brightness to determine how far away they are. By observing these supernovae at great distances, astronomers hope to map the expansion history of the universe. What they found was unexpected. The supernovae appeared dimmer than anticipated. At first, this might not seem particularly significant, but dimmer light meant greater distance, and greater distance meant that the universe had expanded more than expected over time. When the data was carefully analyzed, a remarkable conclusion emerged. The expansion of the universe is not slowing down. It is accelerating. This discovery was both surprising and profound. It suggested that there is some form of energy permeating space, something that is actively pushing galaxies apart, counteracting the pull of gravity. This mysterious force became known as dark energy. It is difficult to fully grasp what this means because it challenges our everyday intuition. We are accustomed to forces that act through direct interaction, pushing, pulling, colliding. But dark energy does not behave in this way. Instead, it appears to be a property of space itself. As space expands, more of it comes into existence, and with it, more dark energy. This creates a kind of quiet feedback loop. Expansion leads to more space. More space leads to more dark energy. More dark energy leads to faster expansion. And so the process continues, gently accelerating over billions of years. There's something almost serene about this idea. A slow, steady unfolding of space itself, guided by a force that operates silently in the background. Another important truth is just how dominant dark energy is. Current observations suggest that dark energy makes up roughly 70% of the total energy content of the universe. Dark matter accounts for about 25%, and ordinary matter, the stars, planets, and everything we can see, makes up less than 5%. This means that the vast majority of the universe is not only invisible, but also fundamentally different from the matter we are familiar with. It is a humbling realization. The world we experience, the stars we observe, the galaxies we admire, they're only a small part of a much larger, more complex reality. The discovery of dark energy was not the result of a single observation, but the culmination of careful work by multiple research teams. Two of the most notable groups were led by Saul Perlmutter and Adam Rees, along with Brian Schmidt. Their independent studies, using different datasets and methods, arrived at the same conclusion. The universe is accelerating. This convergence of evidence made the result difficult to dismiss. It was not a single anomaly, but a consistent pattern observed across multiple observations. There is something quietly powerful about that. When independent paths lead to the same destination, it suggests that we are uncovering something real. Another layer of understanding comes from the concept of redshift. As light travels through an expanding universe, its wavelength stretches, shifting toward the red end of the spectrum. This is known as redshift, and it provides a measure of how much the universe has expanded since the light was emitted. By studying the redshift of distant galaxies, astronomers can trace the history of cosmic expansion. Combined with supernova observations, this provides a detailed picture of how the expansion rate has changed over time. And once again, the conclusion points to acceleration. It is as though the universe, after billions of years of expansion, has begun to speed up, driven by something that permeates every corner of space. Another subtle but important clue comes from the study of the cosmic microwave background. This faint glow, left over from the early universe, carries information about the conditions that existed shortly after the Big Bang. By analyzing its patterns, scientists can infer the overall geometry and composition of the universe. The data suggests that the universe is flat, meaning that its overall geometry follows the rules of Euclidean space. But when scientists account for the amount of matter present, both ordinary and dark, it falls short of what is needed to achieve this flatness. Something else must be contributing. Dark energy provides the missing piece. It fills the gap, bringing the total energy density of the universe to the level required for a flat geometry. This is another example of how different lines of evidence, supernovae, redshift measurements, cosmic background radiation, all converge on the same conclusion. There is a quiet harmony in this alignment, a sense that, even in the face of mystery, the universe reveals its structure through consistent patterns. As you let these ideas settle, there's a gentle shift in perspective. The universe is not just expanding, it is accelerating, not just moving, but being gently pushed outward by something that exists everywhere, yet remains unseen. And like dark matter, dark energy invites us to reconsider what we mean by reality. It suggests that space itself is not empty, but filled with something subtle, something dynamic, something that shapes the very evolution of the cosmos. As the mind begins to relax into this thought, there's no need to fully understand it. It is enough to simply observe, to imagine, to let the idea unfold slowly. A universe expanding, a force unseen, a quiet acceleration, carrying galaxies ever farther apart. As the idea of an accelerating universe settles gently into place, there's a quiet shift in how we begin to picture space itself. It is no longer a passive stage where galaxies drift apart. Instead, space becomes active, stretching, expanding, and carrying everything with it in a slow, steady motion. One of the most subtle yet profound truths about this expansion is that it does not behave like an explosion in the traditional sense. Galaxies are not flying outward into empty space from a central point. Rather, space itself is expanding everywhere all at once. Every region of the universe grows larger, and the distances between galaxies increase as a result. This idea is often described through the concept of the metric expansion of space, a prediction rooted in general relativity. According to this framework, gravity is not simply a force pulling objects together, but a manifestation of how mass and energy shape the geometry of space-time. Dark energy, in this context, appears as something that alters that geometry, causing space to expand at an increasing rate. There is something quietly mesmerizing about this. The very fabric of reality is not fixed, but dynamic, responding to influences we are only beginning to understand. Another gentle realization comes when we consider how this expansion affects different scales. On smaller scales, within galaxies, or even clusters of galaxies, gravity is strong enough to hold structures together. The expansion of space does not pull apart stars from galaxies or planets from stars. These systems remain bound, stable, and largely unaffected by the cosmic stretching. But on larger scales, between galaxy clusters, the effect becomes dominant. Over billions of years, galaxies drift farther and farther apart, their light taking longer to reach us, their presence gradually becoming more distant. This creates a universe that is both connected and dispersing at the same time. Another fascinating detail lies in how astronomers quantify this expansion through the Hubble constant. This value describes how quickly galaxies are moving away from each other as a function of distance. However, even this measurement carries its own quiet mystery. Different methods of calculating the Hubble constant, using nearby supernovae versus observations of the early universe, have produced slightly different results. This discrepancy, known as the Hubble tension, suggests that there may be aspects of cosmic expansion we do not yet fully understand. It is a gentle reminder that even within well-established frameworks, there is still room for discovery. Another subtle but important concept is the idea of vacuum energy. In quantum physics, even empty space is not truly empty. It is filled with tiny fluctuations, brief, transient events where particles and energy appear and disappear. This underlying energy of space itself could be related to dark energy. If dark energy is indeed a form of vacuum energy, it would mean that every point in space carries a small amount of energy. Individually, this energy would be negligible, but across the vastness of the universe, it would add up to something immense, enough to drive the accelerated expansion we observe. There is something quietly poetic about this. The emptiness of space, far from being nothing, becomes a source of motion, a subtle force shaping the entire cosmos. Another possibility is that dark energy is not constant, but dynamic. Some theories propose that it could change over time, evolving as the universe expands. This idea, sometimes referred to as quintessence, suggests that dark energy might be a field, something that varies across space and time, rather than remaining fixed. If this is true, it could have profound implications for the future of the universe. It might mean that the acceleration we observe today could change, either increasing, decreasing, or even reversing under certain conditions. But for now, observation suggests that dark energy behaves very much like a constant, steady, uniform, and persistent. Another quiet truth emerges when we consider how dark energy influences the ultimate fate of the universe. If the acceleration continues indefinitely, galaxies will drift farther apart, eventually moving beyond each other's observable horizons. Over immense stretches of time, the universe could become increasingly isolated, with each galaxy existing alone in its own region of space. This scenario is sometimes referred to as the Big Freeze, where the universe continues to expand, cooling and thinning out over time. Stars will eventually burn out. New star formation will slow and eventually cease. And the universe will become darker, quieter, and more diffuse. Yet, even in this scenario, there is a certain calm. The process unfolds over timescales so vast that it feels almost timeless, a slow transition rather than a sudden end. Another, more speculative possibility is the Big Rip. If dark energy were to become stronger over time, its repulsive effect could eventually overcome all forms of gravitational binding. Galaxies will be torn apart, then stars, then planets, and ultimately even atoms. However, current evidence does not strongly support this scenario. It remains a theoretical possibility, a reminder of how much we still have to learn. As you let these ideas drift through your mind, there's no need to dwell on endings. The universe, in its vastness, is not defined by a single outcome. It is a process, an unfolding story shaped by forces both known and unknown. Another gentle realization is how recent this discovery truly is. For most of human history, the idea of an accelerating universe did not exist. It is only within the last few decades that we have come to understand the role of dark energy. This means that we are still at the very beginning of this exploration. There are new observations to be made, new theories to be tested, new questions waiting quietly to be asked. And perhaps, in time, a deeper understanding will emerge. As the mind begins to settle, you can imagine the universe continuing its quiet expansion, galaxies drifting apart, space stretching gently, the unseen influence of dark energy guiding everything forward. There is no urgency in this motion, only a steady, persistent unfolding. A universe not just expanding, but accelerating, carried by a force that remains invisible, yet profoundly real. And within that vast, quiet expansion, there is a sense of stillness. A reminder that even the greatest mysteries can be approached with patience, curiosity, and a calm, open mind. Chapter 7: A Universe Accelerating. How dark energy shapes reality. There's a quiet shift that happens once we move beyond the discovery of dark energy and begin to consider its consequences. It is no longer just a distant concept tied to supernova observations or cosmological measurements. Instead, it becomes something deeply woven into the fabric of reality itself, something that influences not only the future of the universe, but the way it behaves in the present moment. To understand this, it helps to begin with a simple idea. Expansion is not just something that happened in the past. It is happening now, continuously, everywhere. Every second, the universe grows slightly larger. The space between galaxies stretches, carrying them farther apart. And this process is not slowing. It is accelerating, driven by the persistent influence of dark energy. One of the most profound consequences of this acceleration is the idea of a cosmic horizon. Just as there is a limit to how far we can see on Earth due to the curvature of the planet, there is also a limit to how far we can observe in the universe. Light travels at a finite speed, and because the universe is expanding, there are regions so distant that their light will never reach us. This boundary is known as the observable universe. Beyond it lies more the same, more galaxies, more structures, more cosmic web, but forever out of reach. And as the expansion accelerates, this horizon effectively shrinks in terms of what we can access. Galaxies that are currently visible may eventually move beyond this sima, their light stretched and faded until it can no longer be detected. It is a subtle but powerful idea. The universe is not just expanding, it is gradually becoming less observable. Another quiet truth is how dark energy affects the large-scale geometry of the universe. As mentioned earlier, observations suggest that the universe is flat. This means that on the largest scales, parallel lines remain parallel, and the rules of Euclidean geometry apply. But maintaining this flatness requires a precise balance of energy density. Dark energy provides that balance. Without it, the universe would either curve inward, leading eventually to collapse, or curve outward, expanding too rapidly for structures to form. Instead, it exists in a delicate equilibrium, expanding yet structured. There is something quietly harmonious about this balance. Another fascinating aspect is how dark energy influences time itself, not directly, but through its effect on expansion. As the universe expands, the rate at which distant events appear to occur changes. Light from distant galaxies becomes increasingly redshifted, stretched to longer wavelengths. This not only shifts the color of the light, but also affects how we perceive the passage of time in those distant systems. Events appear slower, more stretched out, as if time itself is being gently pulled apart. It is not that time is changing locally, but rather that our observation of distant events is influenced by the expansion of space. This creates a universe where distance and time are deeply interconnected. Another subtle consequence of dark energy is how it affects the growth of structure. In the early universe, gravity dominated. Matter clumped together, forming galaxies, clusters, and the cosmic web. But as dark energy became more dominant, its repulsive effect began to counteract gravity on large scales. This slows the growth of new structures. Clusters still form, galaxies still merge, but the overall rate of structure formation decreases. The universe transitions from a phase of growth to a phase of gradual separation. It is as though the universe is slowly shifting from building to dispersing. There is a calmness in this transition, a sense that the universe, after billions of years of formation and evolution, is entering a quieter phase. Another intriguing idea is the concept of dark energy's equation of state. This describes how the pressure of dark energy relates to its energy density. In simple terms, it helps determine how dark energy behaves as the universe expands. Observations suggest that dark energy has a negative pressure, something quite unusual. While most forms of matter and energy resist compression, dark energy appears to do the opposite, driving expansion instead. This negative pressure is what allows it to overcome gravity on large scales. It is a concept that feels almost counterintuitive, and yet it fits remarkably well with observations. Another quiet truth is how uniform dark energy appears to be. Unlike matter, which clumps into galaxies and clusters, dark energy seems to be evenly distributed throughout space. It does not form structures. It does not gather. It simply exists everywhere with roughly the same density. This uniformity is part of what makes it so difficult to study. There are no localized concentrations to observe, no direct interactions to measure. Its presence is inferred only through its large-scale effects. And yet, those effects are profound. Another layer of understanding comes from how dark energy interacts with dark matter. While dark matter pulls structures together, dark energy pushes them apart. These two components, together, shape the evolution of the universe. In the early universe, dark matter dominated, allowing structures to form. In the present era, dark energy has become dominant, driving accelerated expansion. This shift marks a transition in the universe's history, a change in the balance of forces that will continue to influence its future. There is something quietly poetic about this interplay. Two unseen components, working in opposition, shaping the same reality. One building, one dispersing, and between them, the visible universe unfolds. As you continue to drift through these ideas, there is a sense of scale, of forces operating across billions of light years, over billions of years, shaping everything from the largest clusters to the faintest galaxies. And yet, all of it unfolds in silence. No sound, no emotion, only the steady expansion of space, guided by an energy we cannot see. Another subtle realization is how this affects our place in the universe. We exist in a time when galaxies are still visible, when the cosmic web is still connected, when the light from distant structures continues to reach us. In the far future, this may no longer be the case. Future observers, if they exist, may see a much darker universe, with fewer visible galaxies, unaware of the vast structures that once existed beyond their horizon. It is a gentle reminder of the uniqueness of our moment in cosmic history. As the mind begins to settle, there is no need to fully grasp every detail. It is enough to simply observe the pattern, a universe expanding, an unseen energy guiding that expansion, a gradual shift from connection to separation, and within it all, a quiet, steady motion, one that continues moment by moment across the vastness of space. As the quiet expansion of the universe continues to stretch across your thoughts, there's a gentle shift from understanding dark energy as a discovery to experiencing it as a constant presence. It is not something that appears suddenly or acts dramatically. Instead, it works in the background, steady, uniform, and persistent, subtly shaping the rhythm of the cosmos. One of the most intriguing consequences of this acceleration is how it changes the long-term visibility of the universe. Right now, when we look into the night sky, we can observe distant galaxies whose light has traveled for billions of years to reach us. That light carries stories of formation, of motion, of cosmic history unfolding across vast distances. But as dark energy continues to drive expansion, something quiet begins to happen. The light from distant galaxies becomes increasingly stretched. Over time, it shifts beyond the visible spectrum into longer wavelengths, infrared, then microwave, and eventually beyond detection. These galaxies do not disappear in a sudden sense. Instead, they fade, slowly slipping beyond the limits of what we can observe. It is like watching distant lights dim into the horizon, not because they are turning off, but because the space between us and them continues to grow. Another subtle truth is how this affects cosmic communication. If two galaxies are separated by enough distance, the expansion of space can carry them apart faster than light can travel between them. This does not violate the laws of physics because it is not the galaxies moving through space faster than light. It is space itself expanding. But the result is the same. Signals sent from one galaxy will never reach the other. In this way, the universe becomes increasingly disconnected over time. There is a quiet isolation that emerges, not suddenly, but gradually, as distances stretch and connections fade. And yet, on smaller scales, there is still cohesion. Our local group of galaxies, including the Milky Way and its neighbors, remains gravitationally bound. These galaxies will continue to interact, merge, and evolve together, largely unaffected by the expansion of the universe. In fact, the Milky Way is expected to merge with the Andromeda Galaxy in several billion years, forming a new, larger galaxy. This local stability provides a kind of contrast to the larger cosmic trend. While the universe as a whole expands and disperses, smaller systems remain connected, forming islands of structure within an ever-growing sea of space. Another fascinating consequence of dark energy is how it influences the concept of entropy, the measure of disorder or randomness in a system. As the universe expands, Energy becomes more spread out, less concentrated. Stars burn through their fuel, galaxies become more isolated, and the overall energy density decreases. This gradual dispersal contributes to an increase in entropy over time. In the distant future, the universe may approach a state of maximum entropy, a condition where energy is evenly distributed and no significant processes remain to drive change. This idea is often associated with the concept of heat death, but rather than imagining it as an ending, it can be thought of as a quiet equilibrium, a state where the universe reaches a kind of stillness with no gradients, no flows, no contrasts. There's a calmness in that image. Another subtle but important aspect is how dark energy influences the passage of time on cosmic scales. As expansion accelerates, the intervals between significant cosmic events grow longer. Star formation slows, galaxy interactions become less frequent, and the overall pace of change diminishes. The universe does not stop evolving, but its evolution becomes more gradual, more stretched out over time. It is as though the cosmos itself begins to slow its rhythm, moving toward a quieter, more shant state. Another layer of understanding comes from considering how dark energy might connect to deeper physical theories. Some scientists explore the idea that dark energy could be linked to the underlying structure of space-time at the quantum level. Others consider modifications to gravity, suggesting that what we interpret as dark energy might arise from changes in how gravity behaves over vast distances. These ideas are still being developed, tested, and refined. And yet, they all share a common theme: the recognition that our current understanding is incomplete. There is more to discover, more to understand. Another general realization is how recent this knowledge truly is. Just a few decades ago, the idea of an accelerating universe was not part of our understanding. Today, it is a central component of cosmology. This reminds us that our picture of the universe is always evolving. What seems mysterious today may become clearer tomorrow, and new mysteries will take their place. As you continue to drift through these thoughts, there is no need to resolve every question. The beauty of this subject lies in its openness, in the way it invites curiosity without demanding immediate answers. Another quiet truth is how dark energy shapes not just the future, but our perspective on the present. Knowing that the universe is expanding and accelerating changes how we think about distance, time, and connection. It reminds us that everything is part of a larger process, one that unfolds continuously beyond the scale of everyday experience. And yet, within that vast process, there is still structure, still motion, still light. As the mind begins to settle, you can imagine the universe continuing its quiet expansion, galaxies drifting apart, light stretching across space, the unseen presence of dark energy guiding everything forward. There is no sudden change, no dramatic shift, only a steady, gentle unfolding. A universe shaped not only by what we can see, but by what we cannot. And within that unseen influence, there's a quiet continuity, a reminder that even the most mysterious forces can be part of a larger, harmonious whole. Chapter 8, The Fabric of Space-Time and the Influence of the Unknown. There's a quiet shift that happens when we begin to think not just about what fills the universe, but about the very stage on which everything exists. Space and time, which once seemed like a passive background, begin to reveal themselves as something far more dynamic, something that can stretch, bend, and respond to the presence of energy and matter. This idea finds its roots in general relativity, a theory that transformed our understanding of gravity. Instead of thinking of gravity as a force pulling objects together, this perspective describes it as a curvature of space-time itself. Massive objects like stars and galaxies distort the fabric around them, and other objects move along these curves. It is a subtle yet profound way of seeing the universe. Imagine placing a heavy object on a stretched fabric. The fabric dips, and smaller objects placed nearby roll toward it. This is often used as an analogy for gravity, not because space-time is literally a fabric, but because it helps us visualize how mass shapes the geometry around it. Now, when we introduce dark matter and dark energy into this picture, the story becomes even more intriguing. Dark matter, though invisible, contributes to this curvature. It adds mass to the universe, deepening the gravitational wells that guide the motion of galaxies. Even though we cannot see it directly, its presence is written into the structure of space-time itself. Dark energy, on the other hand, appears to do something very different. Instead of creating curvature that pulls inward, it influences space-time in a way that drives expansion. It is as if the fabric itself is being gently stretched, not from any single point, but uniformly everywhere at once. This creates a universe where space-time is not static, but continuously evolving. Another quiet truth emerges when we consider how time is woven into this fabric. Time is not separate from space. It is part of the same structure, space-time, and it is affected by the same influences. In regions of strong gravity, time passes more slowly. Near massive objects, clocks tick at a different rate compared to those far away. This effect, known as gravitational time dilation, has been measured and confirmed even within our own solar system. It is a reminder that time itself is not absolute. It flows differently depending on the curvature of space-time. Now, when we consider the large-scale structure of the universe, shaped by dark matter and influenced by dark energy, we begin to see that time on cosmic scales is also part of this evolving geometry. As the universe expands, the intervals between distant events stretch. Light takes longer to travel. Processes unfold over increasingly vast durations. There is a quiet expansion not just of space, but of time as we perceive it. Another fascinating aspect is how space-time can carry waves, ripples that travel through the fabric itself. These are known as gravitational waves, first predicted by Albert Einstein and detected a century later by advanced observatories. These waves are generated by massive, accelerating objects, such as merging black holes or neutron stars. As they pass through space, they stretch and compress distances ever so slightly, creating a subtle vibration in the fabric of reality. While gravitational waves are not directly related to dark energy, they're influenced by the overall structure of space-time, which dark energy helps shape. As the universe expands, the wavelengths of these waves can also stretch, carrying information about the conditions through which they have traveled. It is another way in which the unseen influences the observable. Another gentle realization is how empty space is not truly empty. In classical physics, a vacuum was thought to be a complete absence of matter and energy. But modern physics tells a different story. Even in the emptiest regions of space, There are fluctuations, tiny, transient events where particles and energy briefly appear and disappear. This quantum vacuum is a dynamic environment filled with subtle activity. Some theories suggest that dark energy may be connected to this vacuum energy, that the expansion of the universe is driven, in part, by the energy inherent in space itself. If this is true, it would mean that the very emptiness of space is what drives the cosmos to expand. There is something deeply calming about this idea, that what appears empty is not truly empty, that even in stillness, there is motion. Another layer of understanding comes from the concept of curvature on cosmic scales. The universe, as a whole, can have different geometries. It can be flat, positively curved like a sphere, or negatively curved like a saddle. Observations suggest that our universe is very close to flat, meaning that its large-scale geometry follows familiar rules. But maintaining this flatness requires a balance of energy. Dark matter contributes to gravitational attraction. Dark energy contributes to expansion. Together, they create a universe that is finely balanced, neither collapsing nor expanding too rapidly. There's a quiet harmony in this balance. Another subtle but important detail is how space-time behaves near extreme objects like black holes. In these regions, curvature becomes intense. Space and time are stretched to their limits, creating environments where our usual understanding begins to break down. While dark matter and dark energy play less direct roles in these localized kshetra, they still contribute to the overall structure in which these objects exist. The universe is not made of isolated systems. Everything is connected through the fabric of space-time. Another intriguing idea is that space-time itself may have a deeper structure, something beyond our current understanding. Some theories in quantum gravity suggest that space-time might be composed of discrete units, rather than being continuous. Others propose extra dimensions, hidden beyond our perception, influencing the behavior of gravity and energy. While these ideas remain speculative, they highlight the depth of the mystery we are exploring. Dark matter and dark energy may be clues, signposts pointing toward a more complete understanding of the universe. As you let these ideas settle, there's a sense of quiet openness. The universe is not just a collection of objects. It is a dynamic, interconnected system, a fabric that bends, stretches, and evolves. And within that fabric, unseen forces play a central role. Dark matter shaping curvature, dark energy driving expansion, space and time woven together in a continuous flow. As the mind begins to relax, there's no need to fully grasp every detail. It is enough to imagine, to drift through the idea of a universe where even the emptiness has structure, where space itself is alive with subtle motion, and where the unseen quietly shapes everything. As the quiet idea of space-time continues to unfold, there's a gentle sense that the universe is not built from solid pieces, but from relationships, interactions between energy, matter, and the geometry that holds them together. What once felt like empty distance now begins to feel like something active, responsive, and deeply interconnected. One of the most subtle truths about space-time is that it does not merely exist, it evolves. From the earliest moments after the Big Bang, space-time has been stretching, cooling, and changing its structure. In the beginning, everything was compressed into an extremely dense and hot state. Over time, As the universe expanded, space-time relaxed, allowing matter to form, light to travel freely, and structures to emerge. Dark matter played a quiet role in shaping this evolving geometry, creating gravitational wells that influenced how space curved locally. Dark energy, emerging as a dominant influence much later, began to affect the large-scale behavior of this fabric, gently accelerating its expansion. There's a sense of continuity here. The same fabric that was once compressed into an almost unimaginable density now stretches across billions of light years, carrying galaxies within it like small patterns on an ever-expanding surface. Another fascinating layer of understanding comes from the idea that space-time can store information. In modern physics, particularly in studies of black holes, there is a growing recognition that information about matter and energy is not lost, but encoded in the geometry of space-time itself. While this idea is still being explored, it suggests that the universe retains a kind of memory, a record of everything that has occurred. Even light traveling across the universe carries with it information about its origin, its journey, and the structures it has encountered. And as this light moves through regions influenced by dark matter and dark energy, its path subtly reflects those influences. It is as though the universe is constantly recording itself, writing its history into the very fabric of space-time. Another quiet truth emerges when we consider the concept of expansion at different scales. While we often speak of the universe expanding, this expansion is not something that affects all objects equally. Bound systems, like atoms, planets, stars, and galaxies, remain intact because the forces holding them together are stronger than the effect of expansion. This means that even as the universe grows larger, local structures remain stable. It creates a layered reality. On small scales, there's stability. On large scales, there's expansion. And between these scales, there's a transition, a gradual shift where the influence of dark energy becomes more significant. Another subtle idea is how space-time might behave differently under extreme conditions. In the early universe, shortly after the Big Bang, space-time may have undergone rapid expansion in a process known as inflation. This brief but intense period of expansion smoothed out irregularities and set the stage for the structure we observe today. While inflation is distinct from dark energy, both involve the expansion of space driven by underlying energy. Some theories even suggest that they may be related, representing different phases of the same fundamental process. It is a reminder that the universe may operate through recurring patterns expressed in different ways at different times. Another intriguing possibility is that space-time is not the most fundamental layer of reality. Some theoretical frameworks suggest that space and time themselves may emerge from deeper principles, perhaps related to quantum entanglement or other underlying structures. In this view, what we perceive as space-time could be a kind of emergent phenomenon arising from more basic interactions. If this is true, then dark matter and dark energy might also be manifestations of deeper processes, signals pointing toward a more fundamental understanding of reality. There's something quietly humbling about this idea, that even the fabric of the universe may not be the final layer, that there may be deeper levels waiting to be explored. Another gentle realization is how the expansion of space-time affects the energy of light. As light travels through an expanding universe, its wavelength stretches, reducing its energy. This is why distant galaxies appear redshifted, and why the cosmic microwave background exists as a faint, low-energy glow today. This process is not due to any interaction with matter, but simply the stretching of space itself. It is a quiet transformation. Energy gradually diluted, spread across an ever-growing expanse. Another subtle aspect is how space-time connects distant regions. Despite the vast distances between galaxies, they are all part of the same continuous fabric. There are no true edges or boundaries within the observable universe, only a seamless vista, stretching in all directions. This continuity allows for a kind of unity across the cosmos. Everything exists within the same structure, influenced by the same underlying principles. Another fascinating detail is how dark energy might influence the geometry of space-time in the far future. As expansion continues, the curvature of space-time on large scales may become dominated by dark energy, leading to a universe where local structures remain, but the connections between them become increasingly sparse. Clusters drift apart, filaments stretch and thin, voids grow larger, and the cosmic web gradually fades into a more diffuse structure. There is a quiet transition here, from complexity to simplicity, from connection to separation. And yet, even in this future, the fundamental fabric of space-time remains, still stretching, still evolving. Another layer of reflection comes from a realization that our understanding of space-time is still incomplete. While general relativity describes gravity and large-scale structure with remarkable accuracy, it does not fully integrate with quantum mechanics, which governs the smallest scales. Bridging this gap is one of the great challenges in physics, and it is possible that dark matter and dark energy are part of that bridge, clues that point toward a more unified theory. As you let these ideas settle, there's a sense of openness. The universe is not fully understood. It is still revealing itself, still unfolding. And perhaps that is what makes it so calming to explore. There is no final answer waiting at the end, only deeper layers of understanding, each one leading to new questions. As the mind begins to slow, you can imagine the fabric of space-time stretching quietly, carrying galaxies, light, and unseen forces within it. A vast, continuous expanse, shaped by curvature, guided by energy, and gently expanding, moment by moment, into the unknown. Chapter 9. Simulations and Shadows. Recreating the invisible universe. There is a quiet beauty in the idea that we can recreate the universe, not in its full physical form, but as a carefully constructed reflection built from mathematics, observation, and imagination. In the absence of direct visibility, when something cannot be touched or seen, we turn to simulation. And through these simulations, the unseen begins to take shape. Dark matter, by its very nature, cannot be observed directly. It does not emit light, does not leave a visible trace. And yet, its presence is everywhere, shaping galaxies, clusters, and the vast cosmic web. To understand it, scientists have learned to build entire virtual universes, digital environments where the laws of physics can be applied and observed over cosmic timescales. These simulations begin with something very small, not in size, but in simplicity. They start with the early conditions of the universe, informed by observations of the cosmic microwave background. This faint glow provides a snapshot of the universe when it was only about 380,000 years old, a moment when matter and radiation had just begun to separate, allowing light to travel freely. Within this snapshot are tiny fluctuations in density, variations so small they might seem insignificant. And yet, these fluctuations are the seeds from which all structure grows. In simulations, these initial conditions are translated into a grid of particles, each representing a portion of matter, primarily dark matter. Gravity is then allowed to act, pulling particles together, forming clumps, filaments, and eventually the large-scale structures we observe. What emerges from these simulations is astonishing. Over billions of simulated years, a cosmic web forms. Filaments stretching across vast distances, clusters of matter gathering at their intersections, and enormous voids opening between them. The patterns that arise are not random. They closely resemble the structures we observe through telescopes. It is as though the universe, when guided by the right principles, naturally organizes itself into this intricate network. One of the most well-known examples of this is the Millennium Simulation, a large-scale computational project that modeled the evolution of the universe using billions of particles. The results revealed a detailed cosmic web, complete with galaxy clusters and filamentary structures that matched observational data with remarkable accuracy. There is something deeply satisfying about this alignment. It suggests that even though we cannot see dark matter directly, we understand enough about its behavior to recreate its effects. Another important aspect of these simulations is how they incorporate different types of matter. Dark matter forms the backbone, the primary structure upon which everything else builds. Ordinary matter, including gas and stars, is added into the simulation with additional physical processes, such as cooling, heating, and star formation. This creates a layered model of the universe, where dark matter provides the gravitational framework and ordinary matter fills in the visible details. The interaction between these components is complex. Gas flows along dark matter filaments, cooling and condensing to form stars. Galaxies emerge, evolve, and sometimes merge. Feedback from stars and black holes can heat surrounding gas, influencing future star formation. All of this unfolds within the underlying structure defined by dark matter. Another subtle truth is how sensitive these simulations are to initial conditions. Small changes in the early density fluctuations can lead to different outcomes over billions of years. This sensitivity reflects the complexity of gravitational systems, where small differences can grow over time. And yet, despite this sensitivity, the overall structure remains consistent. Filaments form, clusters emerge, voids expand. It is as though the universe has a preferred way of organizing itself, guided by the interplay of gravity and expansion. Another fascinating layer comes from the inclusion of dark energy in these simulations. When dark energy is added, the expansion of the universe accelerates, affecting how structures grow over time. Clusters become less likely to merge, filaments stretch, and the overall growth of structure slows. This allows scientists to study not just the present state of the universe, but its evolution across time, how it has changed, and how it might continue to change in the future. There's a quiet power in this ability. To watch billions of years unfold in a matter of hours or days. To observe the birth and evolution of cosmic structures within a controlled environment. Another important detail is how simulations help test different theories of dark matter. By adjusting the properties of dark matter particles, such as their mass, speed, or interaction strength, Scientists can observe how these changes affect the resulting structure. Some models produce universes that closely resemble our own. Others do not. This allows researchers to narrow down the range of possible properties that dark matter could have. It is a process of refinement, of gradually aligning theory with observation. Another subtle but meaningful aspect is how these simulations reveal the presence of substructures. Within larger dark matter halos, smaller clumps, subhalos form. These subhalos may host dwarf galaxies, or in some cases, remain completely dark, containing no visible matter at all. This suggests that the universe may contain countless invisible structures, nested within larger ones, forming a hierarchy of complexity. There is something quietly mesmerizing about this idea. A universe filled not just with visible galaxies, but with hidden layers of structure extending far beyond what we can observe. Another general realization is how simulations bridge the gap between theory and observation. They provide a way to test ideas, to explore possibilities, and to understand how different components of the universe interact over time. They allow us to ask, what if, and see the results unfold. And in doing so, they bring the invisible a little closer to understanding. As the mind begins to relax into these concepts, there's a sense of quiet creativity. The universe, in all its complexity, can be explored not only through observation, but through reconstruction, through careful modeling that captures its essential behavior. And within these simulations, dark matter takes shape, not as something seen, but as something understood. A guiding presence, a structural foundation, a quiet force that shapes the universe from within. As these virtual universes continue to unfold in silence inside powerful computers, there's a quiet realization that simulation is not just a tool, it is a kind of bridge. A bridge between what we can observe and what we cannot, between light and shadow, between certainty and possibility. When scientists refine these simulations, they are not simply trying to recreate what we already know. They are testing the boundaries of knowledge itself. They adjust parameters, introduce new physics, and observe how the universe responds. Each variation becomes a question asked in a different way. And sometimes the universe answers. One of the most fascinating outcomes of these simulations is how naturally galaxies begin to form within dark matter halos. As dark matter collapses into dense regions, it creates gravitational wells, deep pockets where ordinary matter can gather. Gas flows inward, cooling as it does, eventually forming stars. In these digital environments, galaxies are not placed manually. They emerge, they evolve, they interact. It is a quiet, organic process, guided by equations rather than direct instruction. This emergence is one of the strongest pieces of evidence that our understanding of cosmic structure is on the right path. When simple physical rules lead to complex, realistic outcomes, it suggests that those rules are capturing something fundamental about reality. Another subtle but powerful insight comes from how simulations handle time. In a real universe, billions of years pass slowly, far beyond human perception. But in simulations, time can be accelerated. Scientists can watch the entire history of the universe unfold, from early density fluctuations to the formation of galaxies and clusters, in a relatively short span. This ability reveals patterns that would otherwise remain hidden. It allows us to see not just what the universe is, but how it became what it is. Another fascinating detail is how simulations reveal the importance of feedback processes. When stars form, they do not remain passive. They release energy through radiation, stellar winds, and supernova explosions. This energy can heat surrounding gas, pushing it outward and regulating further star formation. Similarly, supermassive black holes at the centers of galaxies can release enormous amounts of energy, influencing the behavior of entire galaxies. In simulations, including these feedback processes is essential for producing realistic results. Without them, galaxies can grow too quickly, becoming more massive than what we observe. This highlights an important truth. The universe is not shaped by a single force, but by the interplay of many processes, each one contributing to the whole. Dark matter provides structure. Ordinary matter forms stars and galaxies. Feedback processes regulate growth, and dark energy influences the overall expansion. Together, they create a dynamic, evolving system. Another quiet realization comes from the limits of simulation. Despite their sophistication, simulations are still approximations. They rely on assumptions, simplifications, and computational constraints. Not every detail can be captured. Not every interaction can be modeled perfectly. And yet, even within these limitations, they provide remarkable insight. They allow us to test ideas that would otherwise remain purely theoretical. They help us understand which models are consistent with observation and which are not. Another intriguing aspect is how simulations are used to predict phenomena that have not yet been observed. For example, simulations suggest the existence of numerous dark matter subhalos, small clumps that may not contain any visible matter. Detecting these structures directly is challenging, but their predicted presence guides observational efforts. Astronomers can look for subtle effects, such as distortions in gravitational lensing, that might reveal these hidden clumps. In this way, simulations do not just reflect reality. They help shape the search for new discoveries. Another gentle truth is how visualization plays a role in understanding. The data produced by simulations is often translated into images and animations, showing the evolution of the cosmic web in stunning detail. Filaments glow, clusters form, voids expand, all rendered in a way that allows the human mind to grasp structures that are otherwise too vast to tasawwur. These visualizations are not just scientific tools. They're also deeply calming. They reveal a universe that is structured, flowing, interconnected. A universe that evolves slowly, guided by underlying principles. Another fascinating detail is how simulations explore alternative models of dark matter. What if dark matter particles are lighter, heavier, faster, more interactive? Each variation produces a different kind of universe. Some models lead to smoother structures, others to more clumpy distributions. By comparing these outcomes with real observations, scientists can narrow down the possibilities. It is a process of elimination, a gradual refinement of understanding. Another subtle but meaningful aspect is how simulations connect to observation through surveys. Large observational projects map millions of galaxies, creating detailed catalogs of their positions and properties. These catalogs can be compared with simulation outputs, allowing scientists to test how well their models match reality. When the match is close, confidence grows. When discrepancies appear, new questions arise. And so the cycle continues. Observation informs simulation. Simulation informs theory. theory guides new observation. It is a quiet, ongoing dialogue between what we see and what we imagine. As the mind begins to settle into this rhythm, there's a sense of harmony. The universe is not something we simply observe. It is something we explore, reconstruct, and understand through multiple pathways. Another gentle realization is how these simulations remind us of our place within the cosmos. We are part of the same universe we are modeling. The same laws that govern distant galaxies also govern the atoms within us. There is a continuity that stretches from the smallest scales to the largest. And within that continuity, dark matter and dark energy play their quiet roles. Invisible, yet essential. Unseen, yet deeply influential. As you drift through these final thoughts of the chapter, imagine the universe unfolding not just in reality, but within these silent simulations. Patterns emerging, structures forming, time flowing gently forward. A universe recreated, a shadow of reality, revealing its hidden truths. And within that shadow, a deeper understanding begins to take shape. Chapter 10. The Fate of Everything. Dark energy and the end of the cosmos. There's a quiet stillness that comes when the mind begins to wonder not just how the universe works, but where it is going. The stars above, the galaxies beyond, the vast structures of the cosmic web. They all feel permanent, steady, almost timeless. And yet, everything is part of a larger unfolding, guided by forces that extend far beyond what we can see. Dark energy, with its gentle yet persistent influence, plays a central role in shaping that future. To understand the fate of the universe, it helps to begin with a simple idea. Expansion is not slowing. It is accelerating. And this acceleration is not temporary. Based on current observations, it appears to be a lasting feature of cosmic evolution. This changes everything. In earlier models of the universe, there were different possible endings. If gravity were strong enough, it might eventually halt expansion and pull everything back together in a big crunch. If expansion continued at a steady rate, the universe might expand forever, gradually cooling and thinning out. But with dark energy in the picture, a new scenario becomes dominant. A universe that expands faster and faster over time. A universe where distances grow so large that even light struggles to keep up. One of the most widely accepted outcomes of this process is known as the Big Freeze. Despite its dramatic name, it is not a sudden event. It is a gradual transition, a slow fading of activity as the universe expands and energy becomes more diffuse. Over billions and trillions of years, stars will continue to burn, converting hydrogen into heavier elements, releasing light and heat. But eventually, the fuel that powers these stars will run out. Star formation will slow. New stars will become increasingly rare. And the night sky, once filled with countless Nipotun of light, will begin to grow darker. Another subtle but important detail is how galaxies themselves will change. As dark energy drives expansion, galaxies that are not gravitationally bound to us will drift farther away. Over time, they will move beyond our observable horizon, their light stretched and weakened until it can no longer reach us. What remains will be our local group of galaxies, bound together by gravity. Within this samud, interactions will continue. Galaxies will merge, forming larger structures. Stars will orbit, evolve, and eventually fade. But beyond this local region, the universe will become increasingly empty. There's something quietly profound about this image. A vast universe, once richly connected, gradually becoming more isolated. Another gentle truth is how long these processes take. The timescales involved are almost beyond comprehension. Trillions of years, quadrillions, numbers so large they lose their intuitive meaning. And yet, within these immense spans of time, the universe evolves slowly, steadily, without urgency. Another fascinating aspect of the Big Freeze is the role of entropy. As the universe expands, energy becomes more evenly distributed. Differences in temperature and density, gradients that drive physical processes, gradually diminish. This leads to a state of maximum entropy, where no significant processes remain to create change. In such a universe, stars no longer shine. Galaxies no longer form. Energy exists, but is spread too thin to do meaningful work. It is a state of quiet equilibrium, not an ending in the dramatic sense, but a gradual settling into stillness. Another possibility, though less likely based on current evidence, is known as the Big Rip. In this scenario, dark energy becomes stronger over time, increasing its repulsive effect. Eventually, it could overcome not just the gravitational binding of galaxies, but also the forces holding stars, planets, and even atoms together. Structures would be torn apart, layer by layer. Galaxies would dissolve. Solar systems would break apart. Matter itself could be pulled beyond recognition. While this idea captures the imagination, observation suggests that dark energy behaves more like a constant, making the Big Rip less probable. Still, it serves as a reminder of how sensitive the universe's fate is to the properties of dark energy. Another subtle realization is how the future of the universe depends on something we do not yet fully understand. We know dark energy exists. We can measure its effects, but we do not know its true nature. Is it constant? Does it change over time? Is it connected to deeper physical principles? These questions remain open, and the answers will shape our understanding of the cosmos. Another quiet truth is how the concept of an end may not be as clear-cut as it seems. The universe does not have a single moment where everything stops. Instead, it transitions gradually, moving from one phase to another. Activity slows, structures fade, and the overall state changes over time. It is less like a conclusion and more like a transformation. As you imagine this distant future, there is no need to feel overwhelmed. The timescales are so vast that they stretch far beyond human experience. For now, the universe is vibrant. Stars are forming. Galaxies are interacting. Light is traveling across billions of years to reach us. We exist in a moment of richness, a time when the universe is full of structure, motion, and light. Another gentle reflection is how this perspective changes our view of the present. Knowing that the universe will evolve, expand, and eventually quiet down adds a layer of appreciation to what exists now. The stars we see, the galaxies we observe, the cosmic web that connects them, all part of a dynamic, evolving system, and all shaped, in part, by the unseen influence of dark energy. As the mind begins to settle, there is a sense of calm in this understanding. The universe is not static. It is not fixed. It is a process, an unfolding journey guided by forces both known and unknown. And within that journey, dark energy quietly shapes the path forward. As the mind continues to drift into the distant future of the universe, there's a quiet shift from imagining events to sensing the gradual fading of activity itself, not as something abrupt, but as a long, gentle dimming, like embers slowly cooling after a fire that has burned for billions of years. Dark energy does not rush this process. It does not tear the universe apart suddenly or violently, at least not in the most likely scenario. Instead, it stretches space steadily, creating a future where distance becomes the defining feature of reality. More still, another fascinating phase in this distant future is sometimes called the degenerate era. In this era, most of the universe's matter exists in the form of stellar remnants, white dwarfs, neutron stars, and black holes. These objects persist for incredibly long periods, slowly cooling or interacting in rare events. Collisions between remnants may still occur, producing occasional bursts of energy, but such events become increasingly rare as distances grow. Dark energy continues its quiet work in the background, expanding space, increasing separation, reducing interaction. Another subtle truth is how black holes themselves evolve. Over extremely long timescales, even black holes are not permanent. Through a process known as Hawking radiation, they can slowly lose mass, emitting tiny amounts of energy over time. For stellar mass black holes, this process takes far longer than the current age of the universe, trillions upon trillions of years. But eventually, even these massive objects may evaporate, leaving behind a universe that is even more diffuse. As expansion continues, the temperature of the universe drops. The cosmic microwave background, once a relatively warm glow, becomes colder and colder, its energy stretched across longer wavelengths. Energy spreads out, becomes less concentrated, less able to drive change. This leads toward a state often described as thermal equilibrium, a condition where there are no significant differences in temperature or energy density. In such a universe, there are no processes left to generate new structure, no gradients to drive motion, only a quiet, uniform expanse. Another gentle realization is how this future reflects the influence of entropy. The universe naturally evolves towards states of higher entropy, greater disorder, greater uniformity. Dark energy accelerates this process by expanding space, allowing energy to disperse more quickly. And yet, this disorder is not chaotic in a dramatic sense. It is calm, still, a kind of quiet balance. Another intriguing thought is how perception itself would change in such a universe. Without distant galaxies, without new stars forming, the sky would look very different. The sense of scale that we experience today, the awareness of a vast, interconnected cosmos, might be lost. Future observers might perceive their universe as small, static, and unchanging, unaware of the immense history that preceded them. There is something quietly humbling in that idea. Another subtle aspect is how dark energy shapes not just the end, but the path toward it. If dark energy remains constant, the universe continues to expand smoothly, leading toward the big freeze. If it changes even slightly, the future could be different, perhaps slower expansion, perhaps more dramatic outcomes. But for now, the evidence points toward a steady, persistent influence, a gentle acceleration that continues indefinitely. Another layer of reflection comes from considering the scale of these changes. These are not events that will happen tomorrow, or even in millions of years. They unfold over timescales so vast that they're almost abstract. And yet, they are part of the same universe we inhabit, the same universe that contains the stars we see tonight. As the mind begins to settle, there's a sense of calm in this continuity. The universe does not rush toward its future. It moves slowly, steadily, guided by underlying principles. Dark energy does not announce itself loudly. It simply continues, expanding space, stretching distances, shaping the long-term evolution of everything. And within that vast, quiet future, there is no need for urgency. Only the gentle unfolding of time, a universe that grows larger, quieter, and more still. A universe where the unseen influence of dark energy continues, even as everything else fades into silence. Chapter 11. Experiments in Silence. The global search for dark matter. There is a particular kind of stillness found deep beneath the surface of the Earth. Far below mountains, shielded by layers of rock, hidden from the constant rain of cosmoparticles that pass through the atmosphere, scientists have built some of the quietest places on our planet. These are not places of emptiness, but of listening, careful, patient listening for something that may pass unnoticed everywhere else. The search for dark matter does not happen in bright observatories or visible experiments alone. Much of it unfolds in silence, in controlled environments where even the smallest disturbance can be detected. Because if dark matter interacts with ordinary matter at all, it does so incredibly rarely. One of the central ideas behind these experiments is simple, yet profound. If a dark matter particle were to pass through a detector and interact, even slightly, it could produce a tiny signal, perhaps a faint flash of light, a minute vibration, or a small release of energy. These signals would be incredibly rare and extremely subtle. And so, scientists create environments where such signals can be distinguished from all other noise. One of the most well-known facilities dedicated to this search is the Gran Sasso National Laboratory, located deep beneath a mountain in Italy. Here, detectors are shielded from cosmic rays, allowing researchers to focus on the faintest possible interactions. Inside these laboratories, the atmosphere is controlled, the materials are carefully selected for purity, and the detectors are often cooled to extremely low temperatures. This cooling is essential. At near absolute zero, thermal motion is minimized, reducing background noise and making it easier to detect tiny energy changes. There's something quietly remarkable about this setup. An entire experiment built around the possibility of a single interaction, a single moment, a single trace. Another major experiment in the search for dark matter is SNOLAB in Canada, located more than 2 kilometers underground. Like Gran Sasso, it provides an environment shielded from interference, allowing for highly sensitive measurements. These facilities often use detectors filled with noble gases, such as xenon or argon. When a particle interacts with these materials, it can produce a small flash of light or free electrons, which can then be detected and measured. The challenge lies in distinguishing these potential dark matter signals from background events caused by natural radioactivity or other sources. To do this, scientists develop increasingly sophisticated techniques. They analyze the timing, energy, and spatial distribution of signals, looking for patterns that might indicate something beyond known physics. Another approach involves cryogenic detectors, which measure tiny changes in temperature caused by particle interactions. In these experiments, A passing particle may deposit a small amount of energy, raising the temperature of the detector by an almost imperceptible amount. Sensitive upkaran can measure these changes, providing another possible way to detect dark matter. Again, the emphasis is on precision, on reducing noise, on creating conditions where even the faintest signal can be observed. Another fascinating method involves searching for dark matter in space. Satellites and telescopes look for indirect evidence, signals that might result from dark matter particles interacting with each other or decaying over time. These signals could appear as excess gamma rays, unusual particle emissions, or other anomalies. One such instrument is the Fermi Gamma Ray Space Telescope, which scans the sky for high-energy radiation. By studying regions where dark matter is expected to be dense, such as the centers of galaxies, scientists hope to detect indirect signatures of its presence. So far, some intriguing signals have been observed, but none have been conclusively linked to dark matter. And so, the search continues. Another subtle truth is how global this effort has become. Scientists from around the world collaborate, sharing data, comparing results, and refining their methods. Experiments are conducted in different locations, using different techniques, ensuring that any potential discovery can be verified independently. It is a quiet, collective effort, a shared pursuit of understanding. Another layer of this search involves particle accelerators, such as the Large Hadron Collider. Here, scientists attempt to create dark matter particles by colliding known particles at extremely high energies. If dark matter particles are produced, they would not be detected directly. Instead, their presence would be inferred from missing energy, energy that is not accounted for by known particles. This requires careful measurement and analysis, ensuring that any missing energy is not due to experimental error or known processes. Again, the process is one of elimination, of narrowing down possibilities. Another gentle realization is how patient this search must be. Unlike many experiments where results can be obtained quickly, the search for dark matter requires long observation times. Detectors may run for months or years, collecting data continuously, waiting for a rare event. There is no guarantee of discovery, only the possibility. And yet, each experiment contributes to our understanding. Even null results, experiments that do not detect dark matter, are valuable. They help rule out certain models, guiding future research. Another subtle aspect is how technology plays a crucial role. Advances in materials science, electronics, and data analysis have made it possible to build detectors of extraordinary sensitivity. As technology improves, so does our ability to explore the unknown. And with each improvement, the boundary between the known and the unknown shifts slightly. As you imagine these experiments, deep underground, quietly operating, patiently waiting, there is a sense of calm in the process. Science does not rush. It observes. It refines. It listens. And in that quiet listening, there is hope. Hope that one day a signal will emerge. A small, unmistakable trace. A moment where the invisible becomes just a little more known. As the quiet search continues across the world, there is a growing sense that we are not just looking for something hidden. We are learning how to listen more carefully. The instruments become more sensitive, the methods more refined, and the patience deeper. Each experiment, whether it detects something or not, adds to a slowly forming picture of the unseen. One of the most remarkable aspects of this global effort is how different approaches complement one another. Direct detection experiments, deep underground attempt to catch dark matter particles as they pass through Earth. Indirect detection searches for signals from space, where dark matter might annihilate or decay. Particle accelerators attempt to create dark matter under controlled conditions. Each method explores a different pathway, and together, they form a network of inquiry covering multiple possibilities. Another quiet truth is how much we have already learned from what has not been found. Many early theories predicted dark matter particles with certain properties, specific masses, interaction strengths, and behaviors. As experiments have become more precise, they have ruled out large portions of this parameter space. This does not mean that dark matter does not exist. It means that it may be more subtle, more elusive, or different from what we initially expected. There is something quietly reassuring about this process. Science does not depend on being right immediately. It depends on refining understanding over time. Another fascinating direction in this search involves ultra-sensitive detectors designed to pick up extremely low-mass particles, such as axions. Experiments like ADMX, Axion Dark Matter Experiment, use powerful magnetic fields to convert axions into detectable photons under specific conditions. These setups are incredibly delicate, requiring precise tuning and careful control. The idea is almost poetic, listening for particles that may not collide, but instead whisper through fields and subtle interactions. Another emerging approach involves using quantum bit technology. Quantum sensors, which can detect extremely small changes in energy or fields, offer new possibilities for exploring dark matter. These technologies are still in development, but they represent a promising frontier, one where the boundaries of physics and engineering meet. Another subtle but meaningful aspect is how the search for dark matter connects different fields of science. Astrophysics, particle physics, cosmology, and even condensed matter physics all contribute to this effort. Each field brings its own tools, perspectives, and insights. It is a reminder that understanding the universe often requires collaboration across disciplines. No single approach is enough on its own. Another gentle realization is how the absence of detection encourages creativity. When expected signals do not appear, scientists begin to explore alternative ideas. Perhaps dark matter interacts even more weakly than anticipated. Perhaps it has properties that make it difficult to detect with current methods. Perhaps it exists in forms we have not yet imagined. To continue moving forward, if dark matter particles occasionally collide or influence one another, this could affect the distribution of matter in galaxies. Observations of galaxy cores and cluster dynamics provide hints that such interactions might exist, though the evidence is still being explored. This adds another layer to the mystery. Dark matter may not be entirely passive. It may have its own quiet dynamics. Another layer of this search involves studying the early universe. Observations of the cosmic microwave background provide clues about the amount and behavior of dark matter shortly after the Big Bang. By comparing these observations with theoretical models, scientists can constrain the properties of dark matter. This approach connects the smallest scales, particle physics, with the largest scales, cosmology. It is a bridge between the very small and the very large. Another quiet truth is how the search for dark matter is also a search for new physics. If dark matter is composed of particles beyond the current standard model, discovering it would open a new chapter in our understanding of the fundamental nature of reality. It would reveal new forces, new interactions, new possibilities. And yet, even without a definitive discovery, the search itself has already advanced our knowledge. It has led to new technologies, new methods, and deeper insights into the universe. Another gentle realization is how this process reflects the nature of exploration. Steady, patient, and filled with quiet possibility. Chapter 12. The Deepest Unknown. Philosophical Reflections on a Dark Universe. There's a gentle stillness that comes at the edge of knowledge. After exploring galaxies, tracing invisible structures, and following the quiet influence of dark matter and dark energy across billions of years, the mind begins to settle into a different kind of space. Not one filled with answers, but one shaped by reflection. Because in the end, the story of dark matter and dark energy is not only a scientific journey, it is also a philosophical one. It asks questions that reach beyond equations and observations, touching something deeper, something about how we understand reality itself. One of the most profound realizations is this. Most of the universe is invisible. Everything we see, the stars, the planets, the glowing clouds of gas, makes up only a small fraction of what exists. The vast majority is composed of something we cannot directly observe, something that reveals itself only through its influence. This challenges a very natural assumption, that reality is what we can see, that what is visible is what is real. But the universe suggests otherwise. It tells us, quietly, that the unseen can be just as important, perhaps even more so, than what is visible. There is something deeply calming in this idea, a reminder that absence does not mean emptiness. Another gentle reflection comes from the way we discover these hidden truths. We do not see dark matter directly. We infer it. We observe its effects, measure its influence, and build an understanding based on patterns and consistency. This process highlights a fundamental aspect of knowledge, that much of what we know is indirect. We do not always observe reality directly, but that does not diminish its beauty. If anything, it deepens it. Another subtle realization is how our perspective shapes what we see. We exist at a particular scale, in a particular place, at a particular moment in cosmic history. Our observations are influenced by these conditions. The tools we use, the wavelengths we detect, the theories we build, all are shaped by our position within the universe. Dark matter and dark energy remind us that there is more beyond our immediate perception, that reality is larger than our senses, and that understanding requires imagination as much as observation. Another gentle thought arises when we consider the nature of existence itself. If most of the universe is composed of something we cannot see or fully understand, what does that say about the nature of reality? Is reality defined by what is observable or by what exists regardless of observation? It is a question that does not have a simple answer, but invites contemplation, a quiet exploration of what it means for something to be real. Another layer of reflection comes from the interplay between certainty and mystery. Science seeks to understand, to explain, to bring clarity. But with each discovery, new questions emerge. Dark matter explains the motion of galaxies, but not its own nature. Dark energy explains acceleration, but not its origin. It is a continuous process. Understanding grows, but so does mystery. There's a balance here, between what we know and what we do not, between clarity and wonder. Another subtle truth is how this balance affects our experience of the universe. If everything were known, if every question had a clear answer, the sense of exploration might fade. But the presence of mystery keeps the universe open, dynamic, and engaging. It invites curiosity. It encourages exploration. It creates space for imagination. Another quiet realization is how small we are within this vast system. And yet, how connected we are. The atoms in our bodies were formed in stars. The laws that govern distant galaxies also govern the matter within us. We are part of the same universe we're trying to understand. There is something deeply grounding in this connection. Another gentle reflection is how the concept of darkness changes in this context. Darkness is often associated with absence, with something lacking or incomplete. But in the universe, darkness can represent presence, something real, something influential, something essential. Dark matter, dark energy, not empty, not void, but fundamental components of reality. This reframing shifts how we think about the unknown. It is not something to be feared. It is something to be explored. Another layer of thought comes from the idea of limits. There may be limits to what we can know, at least with our current tools and understanding. Some aspects of a universe may remain beyond direct observation, accessible only through indirect inference. But even within these limits, there is room for discovery, for refinement, for deeper understanding. As you let these ideas settle, there is a sense of calm in the uncertainty. The universe does not require complete understanding to be appreciated. It invites us to explore, to question, to reflect. And in doing so, it offers something quiet and profound. A sense of connection, a sense of wonder, a sense of being part of something far greater than ourselves. As the journey gently comes to rest, there is a sense that the universe has not been fully explained, but quietly revealed, layer by layer, like a landscape slowly emerging through soft light. The questions remain, but they no longer feel urgent. Instead, they feel like companions, moving alongside thought, inviting reflection rather than demanding resolution. Dark matter and dark energy, in all their mystery, leave us with something deeper than answers. And in that sense, the journey itself becomes part of the answer. Another layer of reflection comes from the idea of presence. Even in a universe dominated by invisible components, there is still light, still structure, still motion. The visible universe, though small in proportion, is rich in detail and complexity. Stars form, shine, and fade. Galaxies rotate and evolve. Light travels across immense distances, carrying information from the past into the present. There is something deeply grounding in this. The unseen may dominate, but the seen still matters. Another quiet thought is how the concept of darkness transforms through understanding. What once might have seemed like emptiness becomes something full of influence, full of presence, full of possibility. Darkness is no longer the absence of light, but a different kind of reality, one that operates beyond our immediate senses. This shift changes not only how we see the universe, but how we relate to the unknown. It becomes less intimidating, more inviting. Another subtle realization is how time frames our understanding. We exist in a moment where the universe is still active, still evolving, still filled with visible structure. In the distant future, much of this will fade as expansion continues and energy becomes more diffuse. But that future does not diminish the present. If anything, it highlights its uniqueness. We are here at a time when the universe can be observed, studied, and appreciated in its richness. Another gentle reflection is how knowledge and mystery coexist. Even as we learn more, the unknown remains. Dark matter and dark energy are not signs of failure in understanding, but markers of where understanding is still growing. They remind us that the universe is not a closed book, but an open one, still being written, still being explored. Another layer of thought comes from the idea of connection. Everything we have explored, the motion of galaxies, the structure of the cosmic web, the expansion of space-time, is part of a single, continuous system. There are no true boundaries, only transitions, only gradients of scale and complexity. And within that system, we are participants. Observers, yes, but also part of the same fabric. Another quiet realization is how calm the universe feels when viewed at this scale. Despite its vastness, despite its complexity, it operates with a kind of quiet consistency. There are no sudden disruptions on cosmic scales, no abrupt endings. Everything unfolds gradually, guided by underlying principles. Dark energy does not rush. Dark matter does not interfere loudly. They shape, guide, and influence in silence. There is a kind of peace in that. As the thoughts begin to settle, there is no need to reach a final conclusion. The universe does not ask for one. It simply exists, vast, layered, and quietly unfolding. And within it, dark matter and dark energy remain. Unseen, yet essential. Mysterious, yet deeply integrated into everything we observe. As you drift into stillness, you can imagine the universe continuing its gentle expansion, galaxies moving apart, light traveling through space, unseen forces shaping everything from within. A vast, silent process, endless, calm, and filled with quiet wonder.